Okay, good morning, everyone. Thank you for joining this workshop, especially this early. Today, we're really excited to start the workshop on structured world models for robotic manipulation in the first edition here at RSS. To start, let me introduce the awesome group of organizers today. We have Wenlong, Kaifeng, Alberta, and myself. My name is Bart. Yunzhu should be here as well later today. And we're here to help you with anything that may come up today. So let's talk about why we're here today. This is a video from Ross Tederick's talk at the Stanford seminar. And, personally, I'm really impressed by the level of dexterity. And I'm not sure if many of us thought we could achieve this in 2025. So the question now is, what is missing and what do we need world models for? And what even is a world model? So one bet that I would take is that sample efficiency, robustness, and maybe even throughput could be improved if we inject stronger priors. So world models could really be any other form of supervision, I would argue. So a few examples of world models that have come to the attention recently. NVIDIA Cosmos introduced this model where we take a single image and ask a video diffusion model what to predict next. I was going to say hallucinate, but really it's trying to imagine what's going to come next. And we can use this as extra training data at scale. 1X had a similar world model or video diffusion model that can imagine next actions of the system. And perhaps more broadly, I think the performance of Gemini Robotics' VLA is also quite impressive. And really this sort of general common sense reasoning of large language models also appears to be a useful prior to inject. Coming to the workshop today, we received a large number of really awesome submissions in relevant areas to world modeling and to world models in general. So the first broad category I would highlight is perception. So we had a number of submissions in the area of trying to perceive and maybe track the world in different ways, implicit and explicit world models. So this remains to be an active debate in the field, whether we need this explicit representation. We also saw work on scaling data, so how to use world modeling to actually increase the scale of data we can get. It remains to be a problem, especially compared to other fields like large language models. So finally, I also highlight this physics-informed sim-to-real and real-to-sim, so creating digital twins with a physics prior. Moving on to the submission statistics, today we will see 14 accepted papers, including 4 orals. Topics include essentially what I just mentioned. So there's explicit, implicit world models, data sets, cross-embodiment learning, physics-informed real-to-sim, and many more. So as for the schedule today, we're more or less on schedule, just a few minutes behind. We'll start with the oral presentations. Each person will have 5 minutes, so please stick to that. I'll keep track of time for you. Then we move on to the invited speakers, have a coffee break at 10:30, one more invited speaker, to then move on to the panel discussion. And finally, and this is a remark I'll share later, for the oral speakers, please come back at 12:25, as we'll announce the award of the workshop. This is the schedule of our awesome set of speakers. So we first start with Jerome Revaud, who will be online, Katerina Fragkiadaki, who's there in the room, Jonathan Tremblay, Chuang Gan, if I pronounce it correctly, Yunzhu Li, and Ambrus. Let's take a brief moment to see if there's any questions. Does anyone have questions about any logistics or details about the workshop today? Of course, you can ask questions later if they come up. So if that's it, let's move on to the oral talks. I believe Flare is online. Could you, let's see. Okay, no, this is working, I think. So yeah, please, our last oral presentation on Flare.
Sorry for all the technical issues. I will present Flare. It's a joint work between NVIDIA, University of Maryland, and UT Austin, and it's robot learning with implicit world modeling. So TLDR is we integrated predictive latent world modeling into robot policy learning also achieved SOTA imitation learning performance on multitask benchmarks, and more importantly, it unlocks joint training on action-free human egocentric videos, and it can make the policy generalized to unseen object with only a few teleoperated demonstrations. So, as a recap, a regular VOA will normally look like this. So you have some visual language models generate some VLM embeddings from observation and language instruction. And then you have an action expert diffusion policy head that takes state and noisy actions and try to predict denoise actions via flow matching or other DP losses. And it consumes the VLM embedding via cross-attention. So what we did is instead of just using state and actions, we give it some future tokens that's like trainable embeddings, and we try to extract from one of the layers, intermediate layers, and then do a future latent alignment loss. And that future latent alignment loss is like, so we will have another VLM to take in a future observation with the language and generate some future visual language latents. And then we will calculate the similarity between that and the latent embedding we extracted from the intermediate layer we extracted. So how does the VLM embedding come from? That will be the next question. So what we think is very key here is that the VLM embedding should be action aware. And how we did that is we actually trained another VLA that's like a simpler one without the large VLM backbone. So it's basically using scalable. And we train it with the normal VLA loss and have an action DIT on these data sets. And then we extract the VLM layer to generate the VLM loss with the future observation. So here's all the performance gains. So a nice 10% gain on both RoboCasa, which is a single arm panda, and the GR1, which is a humanoid one compared to our baselines. And same thing here in real. So all the tasks mostly achieve 90% or higher, which is pretty great. And one of the more impressive one is we can, with this additional loss, we can actually generalize to, we can actually utilize human egocentric data to help the policy learn better. So how does that work is we collect the motivation of doing that, I should say, is because human egocentric data is very cheap to collect. You don't have to wear all those teleop equipments and whatever and use a real robot. And teleoperation data is like much more expensive to collect. So if it's, you can use like human egocentric data and like to reduce the number of teleop data you need to use to train a policy, that would be great. So our testing setting is we have like 150 trajectories of human egocentric videos and 1 or 10 teleop trajectories. And we did the joint training with the flare loss, and our results are showing. So with the flare architecture, but without the loss, we are getting like 30-ish% with only 1 teleop data and 1. But with the 150 human egocentric videos, you can achieve like a 60% even with only 1 single teleop trajectory. And with 10, it will get to like 80%. So yeah, that's about it. And if you're interested, you can scan the QR code for our project page and blog post. Thank you.
Sorry for the difficulties. So we introduced WOMAP, world models for active perception. WOMAP enables grounding of robot policies in the physical world. For example, consider the task of finding a banana in the real world, purely from robot visual observations. To efficiently and accurately localize the target, the robot must be able to interpret visual semantic features connecting language instructions to visual observations. The robot must be able to reason about spatial concepts like occlusions. For example, finding the banana behind the ball. Next, the robot must be able to execute grounded actions, not just on the semantic reasoning space, but in the physical world. And lastly, the policy must be robust to distractors in the environment for generalization to multiple tasks. So this policy struggles with active perception in the settings. For example, evidential line policies, while effective in narrow settings, do not generalize beyond the training distribution and require large quantities of demonstration data, often from an expert. Likewise, foundation models like VLMs, although quite effective in providing useful exploration heuristics, fail to ground these actions in the physical world. This remains a non-trivial challenge in grounding VLMs in the physical world. Hence, the action proposed by the VLMs often have hallucinations in the solutions, which are often not reliable for the robot to execute in the physical world. To tackle these challenges, we introduced WOMAP, word models for active perception. WOMAP consists of 3 core components: a scalable data generation pipeline that enables large-scale data generation with minimal human supervision, a word model training pipeline that leverages dense word distillation to overcome the challenges of training word models into this research area. Lastly, WOMAP introduces an online planning framework that evaluates and grounds the actions proposed by high-level VLMs to be able to enable physical execution in the real world. Together, these components enable generalizable, open vocabulary, embodied active perception. WOMAP combines the reasoning capabilities, the common sense reasoning capabilities of foundation models like VLMs with the physical grounding capabilities of word models to enable robust execution in the real world. We evaluate WOMAP across different environments and different settings to show its strong generalization capabilities. First, WOMAP employs a scalable real-to-same-to-real photorealistic data generation pipeline using Gaussian splatting. In this pipeline, WOMAP trains a Gaussian splatting environment from minute-long videos collected from any device, could be on a robot's camera, could be on a physical human's device or a smartphone camera, and automatically aligns and annotates these videos to be able to label different scenes. Lastly, WOMAP generates photorealistic data generation from diverse novel viewpoints, as shown in the video. Next, we annotate these views densely to provide dense training signals for the word model. As shown in the video here, we're able to identify different objects in the scene all automatically without any human supervision in the process. Secondly, WOMAP tackles word model training in an innovative way. WOMAP trains a rewards predictor alongside a dynamics predictor to be able to reason about the dynamic evolution of the robot's observations without actually executing these actions in the real world. We have an observation encoder, a dynamics predictor, and a rewards predictor that work together to be able to visualize the forward rollout of the dynamics of the environment without actually displaying it to the real world. We leverage dense reward distillations from open vocabulary object detectors to be able to train this reconstruction-free word model without relying on image-level reconstruction, which is often a very difficult task, as shown in previous work. So all of the training occurs in the latent space of the model. So we compress high-dimensional visual observations into a latent space using large-scale pre-trained vision encoders such as DynoV2. Finally, WOMAP enables online planning by evaluating action proposals from a VLM and optimizing its actions using reward gradients from the word model. In this situation here, the VLM is asked to find a mug, and the VLM provides 3 different candidate actions. WOMAP evaluates each of these actions, identify which of these actions are more promising in a real-world setting, and is able to optimize this action to be able to select the best or most promising action. In this case, the second action actually leads to finding the mug, which is the task in this situation. Here we show the deployment on a real robot, and here we can see the robot is able to execute this action and successfully identify the target. Lastly, in the experiment, we run a set of experiments across like 10 different tasks and environments, both in simulation and real world. Although the robot is trained entirely in simulation, the robot is able to like achieve strong performance in the real world. Here we showed the robot and the probability evaluations, where we showed that WOMAP achieves about a 15% performance margin compared to prior work like division policies, as well as other world model formulations. WOMAP also achieves strong sim to real transfer, despite being trained entirely on just Gaussian spot data. We see that WOMAP is able to find the object here across different settings compared to other like VLM-only baselines or like world model-only baselines. While other like policies are affected by distractors in the environment, WOMAP is able to find the better error in this video. Lastly, we evaluate the generalization capabilities of WOMAP, and we show that despite being trained only on nominal conditions, WOMAP is able to generalize to different backgrounds, different lighting conditions, and different like settings with very minimal performance impact. Yeah. And the last evaluation, we actually test the semantic generalization capabilities of WOMAP. So here we evaluate WOMAP on unseen language instructions, on object scening training, for example, finding a yellow object, although the robot is only trained on finding a banana, and also on like unseen objects and unseen instructions, for example, finding the pliers, even if the robot hasn't seen a plier. And here we can see that the robot, WOMAP is able to achieve strong generalization, even as we vary the semantic similarity of these like objects and tasks. This is the last slide here, and we have like a demo of the robot being asked to find a banana in a living room. The robot begins by, So the robot begins by looking at the table to find the object before like looking at the couch to be able to find the banana. So that's the end of the talk. We hope you guys can check out our poster later in the afternoon or later in the morning, as well as the website which is on the slide. Thank you.
Hi, everyone. My name is Ifan. Thanks, everyone, for being here at AAM. So today I'm going to present our recent work, and this is a joint work between me, Tianyi, Aaron, and Jerome. So wait a second. Why is it not moving? Okay, here we go. So yeah, in this work, we are interested in taking a single video of a robot interacting with the environment and then building a faithful world model from it. So in this work, we are assuming everything we're dealing with is rigid. And then after the model is built, we want to be able to predict novel physical interactions accurately. However, building these models is challenging. We only have access to noisy and partial real-world observations, and for example, the physical parameters here are unknown. Right, so to do this, to handle these challenges, we aim to leverage the strong priors given in physics-based simulators and renderers, and build a fully differentiable pipeline such that we can estimate the model parameters just given robot controls, trajectories, and the ground truth observations. And once the fully differentiable pipeline is built, then we can iteratively update the model parameters using essentially gradient descent. So at heart of the problem is which object representation should we use? How can we come up with representations such that we can estimate the geometry, appearance, and physical parameters at the same time efficiently? So we adopt a recently proposed differentiable point-based representation. It is an oriented object surface point cloud, which then be converted to the indicator function of an object representing topology using a differentiable Poisson solver. Then it can be converted to a mesh using a differentiable Marching cubes algorithm, giving us a fully differentiable pipeline here. Then we take this representation and further augment it with the object appearance grid, whose texture properties and et cetera can be directly interpolated onto the mesh. Then the world model parameters would include the oriented point cloud, the appearance grid, the terrain point cloud, and all the other physical parameters. Then building a fully differential pipeline allows us to update theta iteratively. So also to make this estimation process efficient, we also generate reasonable initial object geometry guesses using 3D foundation models from RGB images. And we first evaluate our method in simulation on these 9 objects, and the training data include just one RGBD video of a single robot push along with the robot poses and control forces. Then we evaluate it on 23 diverse testing pushes. Here we're showing some qualitative examples. The bottom row is our predictive videos, which are obtained by taking the optimized world model, applying the robot control forces, and integrating forward in time. And our model is able to predict reasonably well accurate trajectories for these testing pushes. Here are some novel synthesis results as well. Yeah, in terms of the quantitative numbers, our method is able to predict very well for the fairly well for the dynamics parameter identifications for all the objects. Well, the baseline struggles. We also report the trajectory prediction errors, which are the average trajectory errors at the end of all the testing pushes. We report the position or rotation errors at the end of these trajectories, and also the unilateral chamfer distance, which is the distance between the observed object point cloud and the predicted object geometry locations. And again, our method is able to do reasonably well on these trajectories and doing much better than the baseline. We also show evaluate our method in the physical experiments on 3 YCB objects in the real world. Here are some real world examples. And quantitatively, since we don't have access to the ground truth object poses, and so we instead report a unilateral chamfer distance, which matches the magnitudes from the simulated experiments pretty well. Yeah, in conclusion, we propose differentiable rigid object representation that allows us to efficiently learn the shape, appearance, and physical parameters at the same time, and combined with the prior given in physics-based simulators and renderers, we enable predictive and generalizable world models using very little data in novel scenarios. And additional video and code is in this QR code. Thank you so much. I'm ready for questions. Yeah, this is a very good question. I actually had a slide. Yeah, but I don't know if I have time to talk about it. Yeah, so it's a simple tabletop setting, and I want to, generalize this to more challenging scenarios, which I think we could do. We're working on it, and also some other limitation I haven't talked about is like right now it's pretty slow, but we're working on it. But we have ideas, and finally, we're only using simple rendering equations such as RGB, and we're hoping to include more complex rendering equations in there as well. Yeah.
I'm Daniel. I'm very happy to present the work of my colleagues that unfortunately couldn't be here today. DIVA, diffusion policy adaptation with world models. In humans, dreaming is associated with an enhanced ability to solve next-day problems. This ability to sleep on a problem and wake up with clarity inspires this work. Diffusion policies are powerful tools, but they inherit the core limitations of imitation learning and are restricted to the narrow scope of expert demonstrations. Online reinforcement learning can fine-tune policies, but it can be sample inefficient and risky. Needing millions of environment interactions makes it impractical for real-world robots. In this work, we fine-tune diffusion policies entirely offline inside a learned world model. By generating imagined rollouts in latent space, the robot practices in a dream, improving its skills efficiently. The training process of DIVA consists of 4 phases. In the first phase, we train a world model on unstructured play data. This model captures the environment's dynamics in a compact latent space. Next, we encode expert demonstrations into latents and pre-train a latent condition diffusion policy that denoises actions. The world model lacks task rewards, so in phase 3, we train a binary classifier on expert latents to predict success and provide rewards during imagined rollouts. In the final phase, we fine-tune the diffusion policy using policy gradients on imagined rollouts in the dream diffusion Markov decision process, enabling efficient skill adaptation entirely offline. To evaluate our approach on real-world robots, we collected 4 hours of teleoperated play data using a Franka robot in a tabletop setup, recording multiple view observations to train our models. Here we see the first skill, opening a drawer. On the left, the pre-trained diffusion policy often struggles to complete the task. The middle column shows imagined rollouts within the latent space where the robot adapts its behavior offline. And on the right, the fine-tuned policy successfully opens a drawer without any real-world interactions during fine-tuning. Next is the slider task. Again, the pre-trained policy lacks robustness, it misses the handle and fails to complete the task. In the center, we see the policy refining its behavior through imagined rollouts in the latent space of the world model. And in the final column, we see the policy perform a smooth and successful push in the real-world environment. Finally, in the closed drawer task, we observe the same pattern: initial failure, offline fine-tuning in the latent space, and successful execution in the real world. Across all three skills, the robot improves without touching the real world. This highlights the power of our approach, combining diffusion models, policy gradients, and learned world models to adapt skills safely, efficiently, and entirely offline. The graph on the left shows how the policy performs in the real world with respect to the number of world model interactions during fine-tuning. We also report policy improvements across 8 skills in Kelvin's environment D. To achieve a similar improvement across 8 skills, the latest SOTA online diffusion policy fine-tuning baseline requires 2.5 million environment interactions in total. And yeah, that's it. Thank you. And you can reach out to Akshay for any further questions.
So the first speaker will be Jerome Revaud. I'll give like a 3-sentence introduction. Jerome Revaud is a research scientist, or maybe senior research scientist at Naver Labs Europe. He works on 3D foundation models in 3D vision, which are, I believe, are very applicable to the robot world models domain. He is one of the co-authors on seminal papers like Croco V2, Duster, Master, Muster, I think, which is more recent, Power, in general, a bunch of really exciting 3D foundation models. So I'm excited to learn what he has to say today. And Jerome, please, if you can share your screen, we're excited for your talk.
Thank you. So yeah, today I want to talk about the 3R family, a foundation model for 3D vision, or actually a candidate. So in this talk, I will first present where I'm coming from and like my background, the place where I work, and the vision of our lab. And then I explain what my definition of a foundation model for 3D vision is. And essentially, the Duster framework is the answer to this question. So I will present the Duster framework from the pre-training up to the training and to recent extensions. And I will conclude with some final remarks. So Naver Labs is a company which belongs to Naver, a Korean IT company, pretty much like Google, but in South Korea. And Naver Labs is really focused on robots. So Naver Labs built a huge building in South Korea where robots and humans can cohabit. And here you can see one of these robots, which are right now delivering parcels, drinks, food. And so users can, like anywhere in the building, you can order something, the robots will bring it to you, it can navigate, it can take the elevator. But this is like a giant test bed for robotics, right? And I'm working in Naver Labs Europe, which is located in Grenoble, France. This is a really nice place. If you can visit, that would be wonderful. And we really focus on making robots part of our everyday lives. And for that, we undertake a multidisciplinary approach to AI. So I'm a computer vision guy, and I come from the 3D vision field, more specifically. And for this 3D vision, what is it? I would say that it's a collection of different tasks, like, for instance, monocular depth estimation, large-scale 3D reconstruction, point matching, visual localization, multi-view pose estimation, you name it, right? There is a lot of 3D vision tasks. And the commonality between all these tasks that somehow they are all dealing with 3D geometry, camera positions, these kind of things. So far, these tasks have been treated separately, with very dedicated and specialized approaches. And this is really a bit problematic, right? It's not very satisfying because they share a lot in common, yet they are treated with completely different approaches. And if we look at the case of the natural language processing community, it used to be the same. There used to be many different tasks like translation, sentiment analysis, text summarization, question answering, and so on and so forth. And of course, we all know what happened with ChatGPT. Basically, a single model can pretty much zero-shot solve all these tasks. But not only it can solve all these tasks separately, it can also solve any combination of these tasks. And that's really game changer and opens like so many use cases and possibilities, right? So foundation model is I think something we should definitely seek, but there's no real consensus, no real definition of what a foundation model for 3D vision is, right? Here is a non-exhaustive list of proposals, and all of them have some kind of different definitions of what it is. I think everybody agrees that it should be at least like pre-trained with some kind of weakly supervised pretext task, like next token prediction is really useful for downstream task in the NLP community. So basically, my take of what a good foundation model for 3D vision should be is basically a model able to establish correspondences between images, able to infer 3D geometry, either from learned priors, like for instance, in the case of a single image, or from multiple views, like triangulation or something like that. And it should also be able to infer the position of the camera. It should be able to decompose motion, lighting effects, long-term changes. And this leads us to our first work called PROCO. So PROCO is short for self-supervised learning with cross-view completion. And PROCO is a guessing game. It's a very simple game. Given two images, right? We have a reference view and a query view, but the part of the query view has been masked. And the goal is to predict what is hidden behind the mask. And to solve this task, well, you're going to compare the two images, right? You're going to do image matching. You're going to need to estimate the relative pose between the two cameras. And for that, you need some estimation of the depth in the image. You need some priors about shape, like this stone pole has some flat surface with some kind of shape we cannot understand. You need maybe to adjust the color changes because the lighting conditions are different. And if you do that all of that perfectly, then voila, you should be able to accurately predict what is hidden behind the mask. So that's exactly what the pre-training PROCO is. So basically we have this two input views of the same scene, and the query view is randomly masked. And in the middle, we have this big transformer network. So VIT's vision transformer is basically a vanilla transformer that takes patches instead of text tokens. And it outputs, the query image unmasked. And it's trained with a simple L2 loss in the RGB pixel space, right? So when you train such a network on millions of pairs, image pairs, either synthetic or from real data, then this is what you get. So on the left, you have the two input images, and here you have the output, and here the ground truth. And you can see that it's a bit blurry, but definitely it looks like it gets it right. And here, for instance, this brown object is completely masked, but it's still able to infer its existence because it's in the reference view, even though it's a bit blurry, meaning it's not very confident about exactly where it is in the scene, right? And we essentially built on top of Propo to build Duster. So Duster means dense and constrained stereo 3D reconstruction. And this is the same architecture, right? It's exactly the same, except that this time, instead of predicting RGB images, we are predicting point maps. And point maps are explicit 3D representation of the input image. So specifically, a point map is an image, but instead of RGB value for each pixel, you have the X, Y, Z coordinates for this pixel, right? So this is what is represented here as like blue dots and red dots. These are point maps. And to make the problem well posed, we defined these 3D coordinates in the reference frame of the first image, assuming it has an identity pose. And we apply, again, a very simple regression loss, which is scale invariant, because the scene is unknown up to, is known up to a scale factor, right? And again, when you train Duster on millions of image pairs, again, synthetic or from real data, we use typically a mix of both. Then it works, the same model works indoors, outdoors, on close-up objects, on any kind of data. And it even is able to perform tasks that were not possible before. So this impossible matching task is given two images without any overlap. There's not a single pixel shared between these two images. Yet Duster is still able to construct like the correct reconstruction because it has learned many pointers. Like it knows that the ceiling should be aligned, the wall should be aligned. It understands that this is the left, like this should go on the left and this should go on the right because maybe there is a bit of a table here on the other side of the table here and so on, right? So Duster, we actually extended several times. So the first extension we did was with master. It's basically a very simple extension to improve the matching accuracy. And then we were able to solve a hard problem, like hard for a human at least, like this. Given these two images, what is the relation between the viewpoints? It's kind of hard to tell, but actually this pool here is the same as this one, and the viewpoints are opposite, right? And when we apply master on this kind of hard image pairs, we get like really amazing results, like much better than existing matching approaches. Like so good that actually we won the map-free verticalization challenge by a large margin. We got like 80% precision, and the second best was less than 50%. This was last year at ECCB. Right, and here is a like visual demo of, so in red you have the reference image, and the query image is the moving camera. And all these frames are treated separately. There's no temporal smoothing or aggregation, so it's kind of impressive in my opinion, right? And when applied the same model to multi-view stereo, which is like dense 3D reconstruction, we can actually beat handcrafted method, and we perform on par with in-domain, like dedicated approaches for this task and for this data sets. And we actually perform on par while, this is zero shot. We have never seen this data during training. So again, this is like a clear demonstration, like foundation models have this like capabilities of zero shot outperform any dedicated approach. And we further extended master with master SFM. And Bart was one of the authors on this paper. We got the best student paper at 3DV recently. And very quickly, this is like the kind of dense reconstruction we can output from very few images, which I think at the time of submission, like not a single approach we're able to do. So to summarize, the Duster framework, we made 3D vision easy, at least we believe so. It takes an unconstrained collection of images, and constrained means no pose, no intrinsics, and it output point maps, which are essentially dense 2D, 3D mappings. And from these point maps, we can extract, straightforwardly many things. We can recover the camera calibration. We can get depth maps, like for monocular case, for multi-view cases. We can get pixel correspondences, camera poses, and then 3D reconstruction. So is that the end of it? Well, of course not, because there's many real use cases where, for instance, you would have specialized sensors. You have a camera rig, like this case is a street view vehicle that collects street view images, and it has LiDAR. So how to use this additional information? Well, Duster cannot. It just take images as input. Same if you have a robotic arm, you have these two cameras. One of them is still, one of them is attached to the arm. I'm sure you have calibrated very properly your cameras. And so basically, the question is, how can we incorporate additional information into Duster? This is the our paper we recently presented at CVPR. And yeah, I think I already explained the motivation. So the idea is very simple. We start from the Duster architecture, but this time during the training, we optionally provide more information to the encoder and the decoders. So randomly, we input intrinsics, depth, which can be sparse, can be dense, or we also provide relative tone between the cameras. And because this is randomly selected, at test time, the network basically can deal with any combination of information. And we verify that if we just give images, exactly like in Duster, it performs as well as Duster. But if we provide more information, like the intrinsics or the relative pose, then it starts predicting much better results, which makes a lot of sense, right? And not only this is already nice to have improved results if you know the calibration, but you can also do more tasks. Like, for instance, here's something we could not do with Duster. So here you take two images, you put them in Duster, you get some force reconstruction, because Duster works with fixed size resolution. You can extract the depth maps from this first output, and can re-inject that, this time in a sliding window mode, because sliding window is actually parameterized by intrinsics. So for each window, you can specify the parameters of the crop based on the input intrinsics. And then we can, this is the raw output actually. It's basically doing some high resolution reconstruction, in a tiling, sliding window mode. And it can, for instance, also do depth completion based on sparse LiDAR points. So here, this is the new NYU datasets. You have an input image, and you have sparse depth points. And because the method is trained to always output dense outputs, then we get the dense depth map for free, right? And we actually outperform every existing specialized, again, the dedicated method for this task, which is called depth completion. We outperform this zero shot. So so far, the Duster family, or 3R family, we have leveraged large-scale self-supervised training with Croco. We show, I didn't talk about that by lack of time, but we show that this is important to have good performance with Duster and all following works. We made 3D vision simple and flexible, right? All tasks are now covered. But one thing I forgot to mention is that all of that is offline, right? And Naval Labs, we work on robots, but robots live in the present. So we need some online real-time processing, right? that's the last work we have presented last week at CVPR. And the idea of Muster is basically to extend, Duster or Master to some online mode that can also handle videos and basically process images one by one. So again, we start from the Duster architecture. And if I expand the decoder block, which is when the transformers from the first stream and the second stream exchange information, they are composed by a succession of blocks, transformer blocks, with self-attention, cross-attention, and MLT, right? And the cross-attention is here to basically exchange information. So the first stream, is sending its token to the second stream, which is going to incorporate this information, and it continues like that several times. So if we remove one of these errors, we can basically make this method causal in terms of the temporal direction, right? Let's imagine these are frames, frame 1, frame 2, frame 3, and so on. Then this architecture becomes causal because this transformer is only relying on previous frames, not on future frames. Meaning now it becomes basically an online method. So we can train this, right? And this becomes the same decoder. These decoders have shared weights. So in a sense, what we end up with is this very simple architecture where we have an input frame. It goes into the encoder, and the decoder compares this frame with some latent memory, which basically contains the previous frames, and it updates the memories with this new frame. And also it outputs, like a 3D, like a point map for this frame in local frame and also in the global frame, which is defined by the coordinate system of the first image in the sequence, right? So here is a demonstration on a small GPU running on the laptop. This is real time. You have the reconstruction here, and on the right, you have the input video, right? And this is basically the raw output of the method. So you can see that, it's kind of impressive in the sense that there is not a single optimization, like geometric explicit optimization here. It's pure feed forward. There's no bundle adjustment. It's pure regression, right? There's nothing else here. And it's basically doing loop closure in an implicit manner because of the memory, right? When it comes back to something it has seen in the past, then it has to basically fall back on its feet. Again, Muster works for any situation. It works for like large scale outdoor scenes, indoor scenes, like close-up objects, and so on and so forth. And it even works on really large scale. It's not city scale, but it's still quite big. So this is 400 square meter indoor space in a chateau. We have a chateau here at Naval Labs Europe, Castle, French Castle. And you can see the camera is navigating inside. And this is like the real-time output of Muster. And it's a bit noisy. It's clearly not perfect, but the blueprint is correct actually. And to my knowledge, this is the only method that can do that in a feed-forward only manner, right? I know SLAM methods nowadays can definitely do something like that, but SLAM is quite handcrafted a lot, right? And so the nice thing here is that this is pure data-driven, and I'm sure we can further improve on that. So of course, there's a lot of recent works that have expanded the 3R family. There's Spanner also from 3DB. There's Qter, MPDuster Plus, Faster, MasterSlam, Monster. There's the large spatial model. and Raster very recently, where the extension of Duster to predict like the front and back sides of objects. I'm sure there is many more that that are listed here or that I forgot. I'm sorry. So yeah, to conclude, I think Duster is a good candidate for 3D foundation model. It unifies 3D vision tasks, it unifies offline and online tasks, unordered image collections and videos. Of course, there is some remaining problems like semantics. Of course, we need semantics if we have a true foundation model. And accuracy is not yet as good as ColdMap in some situations where you have like lots of images with lots of overlap, lots of texture. And for sure, we are not at this level yet. But I think the gap will be closed soon. And these are very exciting times for 3D vision. So thank you for your attention. And please, if you have any questions, don't hesitate.
Thanks a lot, Jerome. That's a really awesome presentation. Are there any questions in the room? I can bring the microphone to you if you're interested. Okay. Jerome, can you hear this?
Yeah, absolutely.
Yeah. Okay. Yeah.
Hey, thanks a lot. One thing that you did not talk a lot about was actually like the underlying data that you require to train such models. Like,
Right.
Can you say a few words around this? Like, how important is the data? How much curation did you do? Like, how did you go about this?
Yeah. So there's two aspects of this. The pre-training, for the pre-training, this is like a self-supervised task. So you only need to find pairs. And it's kind of easy to make pairs from like, using existing handcrafted approaches. And it's not a big issue if your pairs are sometimes wrong but for training Duster and all subsequent models, we found it was quite important to have like high quality data. And it's true, I didn't really talk about that, and this is a very important aspect. So what we found is that data is really important, right? That's the most important criteria in Duster working well is the quantity of data. That's one thing. Second is that we found it's good to have 50% of synthetic data and 50% of real data. So synthetic data are like really perfect in terms of ground truth, and they serve the model to learn really accurate predictions. Especially, real data, you typically struggle with annotating thin structures or, corners and like edges, these kind of things. So synthetic data are great for that. But with only synthetic data, you have a trouble generalizing to the real world. So having a mix of 50% synthetic and 50% real data is, I think, is a good trade-off. And one last thing is that recently, there is a lot of new data sets about like 3D like scenes. There is mega scenes which contain 1 million landmarks. There is a 361M, which also is like 1 million 360 videos. So there is maybe not such a need to have like unsupervised training. Maybe it's fine to massive like fully supervised training right now. I'm not exactly sure, but yeah, I have been quite surprised by the recent surge of like large-scale data sets in the last year.
Right. Thanks a lot, Jerome. I think we'll move on to the next speaker, but thank you so much for giving the talk.
Thank you.
Okay, hi everyone. So again, for those who just joined, we're running a bit late, but yeah, we are fine-tuning to the workshop. So it's my pleasure to introduce Katerina, our next speaker. So Katerina Fragkiadaki is an assistant professor at the machine learning department at Carnegie Mellon University. And her research combined common sense reasoning with deep visual motor learning for action perception and language grounding. Katerina got her PhD at University of Pennsylvania and she was also a postdoctoral fellow at UC Berkeley and Google. And her work has been widely recognized, including, but not only, with the Best PhD Award and NSF Career Award. So please join me welcoming Katerina, and the floor is yours. Thank you.
Yeah, thank you very much for your invitation and giving me the opportunity to present my work. Do you want me to unmute myself in the Zoom or no? No, do you want me to open my camera or no? Okay. Yeah, so I'm very happy to be right after the Duster author talk because, you know, we're very inspired by this work, and mostly we're going to show, once we're able to get accurate 3D, what can we do with this? How can accurate 3D help robot manipulation? So that's the first part I will discuss. We see robot foundation manipulation policies, okay, coming out over the time, right? Like every week there is a new VLA model, right? Using this fantastic effort, the open source demonstrations of OpenX embodiment dataset and other datasets that are being contributed essentially through behavior cloning, and they try to build this, you know, general instruction following robot manipulators. And many of them follow the following, let's say, architecture. There are a bunch of images coming in that are being encoded with some pre-trained feature backbone. And you know, they're used to denoise essentially trajectories of the grippers and effector. Okay, so often we use diffusion objectives because I mean that was one of the biggest, in fact, revolutions in behavioral cloning. The fact that instead of using regression or VAEs, we have better generative models, super instrumental to handle multimodality in demonstrations. Recently, like about a year ago, we have presented the 3D analog of this architecture, okay, where you have your noise poise estimates, what you see here on the bottom, and instead of building 2D feature maps and using 2D feature maps to denoise those trajectories, you use 3D feature representations. And so I'll show you what are the benefits of that, why this is important, and of course the details matter here of the execution. So the main idea of our what we call 3D diffuser actor, because you know that combines ideas of 3D and diffusion. The main idea is that action tokens and visual tokens live in the same 3D space. So here is how it works. You have your robot that can watch the scene from an RGBD camera, and you take the RGB image, you featurize it, you get a 2D feature map, and every token has a depth. And you can use this depth to unproject those tokens in 3D. And if you have other viewpoints, you can just aggregate those feature tokens. So you have a larger feature cloud. And the idea is that if you have multiple views, those better be calibrated so you know the relative camera pose between those. And then you're going to use this 3D feature cloud to denoise robot trajectories. And specifically, robot trajectories here are essentially gripper orientation and translations on the 3D task space. And so we have two types of tokens here in our denoising transformer. There are the visual tokens, which are exactly those patch features with XYZ coordinates, and we have those action tokens, each one of which will decode essentially a pose for the robot's end effector in the future. And the important idea is that those have positional encodings in the same 3D space. So essentially, we represent the visual tokens in the robot gripper's coordinate space, okay? They need to be in the same space. And because they're in the same space, and we want our model, our 3D denoising transformer, to be translation invariant, we're going to use relative attentions. And relative attentions essentially look like that. Only the difference between the positional encodings of two tokens influence their attention, not the absolute coordinates, because where you set the center of your coordinate frame is absolutely arbitrary, and you don't want your manipulation policy to remember about that. So we have this 3D denoising transformer that essentially, you know, also takes, of course, the language instruction because we're going to be, you know, training multitask manipulation policies. So this is the language instruction. These are the visual tokens, the 3D visual tokens that I described. This is a proprioception of history of proprioception for the robot to know where this robot gripper is. And here are these noise trajectory tokens that are going to decode the trajectory of the robot. Okay, and it's important this trajectory to be in task space as opposed to body joints, because body joints are not in the same space as the 3D visual tokens, right? So this is important. So then once you train by taking essentially trajectories, adding noise to them, and then asking the denoising transformer to predict the noise, at test time you denoise sequentially, and you should go from random noise into a predicted trajectory of the end effector. So here I'm showing 60 samples of that model. I'm only visualizing the translation just for you guys to see. They concentrate around the basic modes of where this gripper is going to go next. Okay, this is just for visualization purposes. And here, I mean, this model can be used to predict continuous trajectories or discrete key poses. And in the second case, you need to use a motion planner to go from one predicted key pose to the next. So here I'm showing 3 key poses. You see, again, we have 60 samples, but they are all concentrated around 3 modes, because at training time, when we collected those demonstrations, sometimes we would pick up the green grape, sometimes the red one, and sometimes the black one. Okay, so you see that our generative model can exactly capture the relevant modes, not drop modes, and not hallucinate new modes. 3D diffuser actor has a very good performance in 2 very different benchmarks: RL bench, which is designed mostly for 3D policies, and Kelvin, that is designed, mostly 2D policies are evaluated. So this shows how general it is, and it has been used by many, other labs. And recently we have extended this to bimanual manipulation. So now you have 2 hands and 2 grippers, and the idea is going to be exactly the same. We're going to also switch from diffusion to flow matching so that we have much faster inference with much fewer number of denoising steps. But the idea is the same. Again, you have a set of 3D visual tokens, and now you have 2 sets of action tokens, one for the left gripper and one for the right gripper, and you have your language conditioning, and then you do iterative denoising, and the denoising looks like that, essentially. So you see the blue. Yeah, so the blue and the green are the 2 grippers, essentially the 2 arms, and you see how fast with only 4 denoising steps we're able to do the inference in that 3D space. You see I mean, this is not a point cloud, this is a feature cloud, but I'm showing a color point cloud for visualization purposes, okay? So our baselines here are going to be pi0, PERAC2, diffusion policy, 3D diffusion policy, ACT, and any bimanual. Pi0 is a, well-known generalist policy that is a 2D. Again, it has a flow matching action decoder. And 3D diffusion policy, interestingly, is very similar name-wise to our policy, but they don't have this core idea of having action tokens and visual tokens on the same space. And in fact, we evaluated 3D diffusion policy here on Kelvin, and it had the lowest performance. You see this blue, little bar, because they just take the point cloud and encode it and attend to it with a point to decode, to denoise the trajectory. So I just want to mention here that 3D policies doesn't mean that instead of taking the image, instead I'm going to look at the point cloud. I think it mostly means how do you reason in 3D space directly during denoising. So every denoising step looks at the 3D tokens in that 3D space and predicts where it needs to go, where the gripper should go. So we adapted, so we wanted to test those baselines in the PERAC2 bimanual benchmark, and we adapted pi0 to predict key poses, because all the other baselines predicted key poses, and this increased its performance. So the results look as follows. On average, 3D flow actor does much, much better than the baselines. You see the average across tasks here, and then I'm showing the performance on some tasks. We made the exact analog of a 2D flow actor. Sorry, I call it diffuser, but it's actually flow actor. I'm sorry about this. And it's the green. So there is a drop if you reason in 2D. Okay, so the action is here, and the 2D visual tokens are in a different 2D space, and the 3D tokens are in the task space, and there is no essentially, in the positional encodings, there is nothing to connect them directly. Okay, so you have a direct drop in performance. Now, another big question is how important is to have multiple cameras, which is completely unrealistic. If you have a robot moving around, you are not going to have 3-4 cameras looking at the scene. And there is not a big drop in performance if you use one camera versus using wrist cameras and external cameras and so on. So the 3D reasoning is the key idea here, as opposed to having multi-view input. Yeah, in comparison to a 3D diffuser actor code, I mean, our 3D flow actor, which soon is going to be released, is going to be much, much faster, much, much easier to train. And yeah, we hope that you guys are going to take a look and you'll find it useful. Now, what about the real world? Why 3D policies have not gone in the real world? So we wanted to do that. So what we got is we got a mobile Aloha with this excellent of a cheap platform that you can very easily collect kinesthetic demonstrations. And we collected 40 demonstrations for each one of those tasks, okay? And again, we're going to predict the end effector trajectories in the task space, same as before. And so, it did reasonably well. So we designed tasks that, both arms are necessary here with ropes and so on and so forth. And we just wanted to figure out what are the challenges of moving these 3D policies from simulation benchmarks to the real world. And I'll tell you what the challenge is. The challenge is the calibration. So calibration means that the robot needs to know where its gripper is in the camera frame, okay? Or it needs to know where the visual token is in its gripper frame. One or the other. So that action tokens, which is the gripper, and visual tokens, which is the scene, right? The RGBD image can be put in the same space for 3D reasoning. And we know calibration, maybe in expensive robots is possible. For this mobile Aloha, it was actually challenging, especially when the gripper is extended. We had 1 to 2 centimeters error on the calibration, no matter what we did. So yeah, in real world, again, 3D diffuser actor is has much better performance and has much faster inference and much fewer parameters than the alternatives, which is 3D policy and Pi 0 here. We were managed to fine tune on the same training data. And I can show you, many failure modes, but I think the important thing to highlight is the calibration problem, right? So you think your gripper is somewhere in the camera frame, but guess what? The gripper is somewhere else. And, all the data sets that come out, Bridge and Droid and, RoboMind and, the IAG bot benchmark, that none of them is calibrated, right? None of them is calibrated. So we can use essentially the robot location in the camera frame, either 2D or 3D. I mean, we're using 3D, but you can also use in the 2D, where the gripper is in the image, essentially. This is what I mean, camera frame. So essentially, we put some effort here on camera calibration to fix that one using machine learning. So what we did is we started with this excellent paper from Coral 24, differentiable robot rendering, where we trained a neural network to map body joints to 3D Gaussians of the robot. I mean, you need to tell me the robot, I'll take the URDF of that robot, I'll go in simulation, render it in different poses and from different views, and then I can train that neural network, right? Through rendering losses. Essentially, the neural network predicts 3D Gaussian parameters, you render Gaussians differentiably, you compute the rendering losses, and you backpropagate to the weights of Dr. Robot. So once you train that model, what you can do is you can go in the real world now, you have a particular video in Droid or Bridge and so on, and your goal is to infer the rotation and translation of the camera in the robot's coordinate frame, okay? So you need to figure out where is the camera taking picture of the robot. Do you see? So, and each time you take a picture, essentially you render those 3D Gaussians for that view, and then you match the RGB, the flow, the point trajectories, and then you can optimize now that transformation holding Dr. Robot neural network frozen. And in this way, we're able to calibrate a lot of videos, okay? Now, having said that, I want to mention that the body joint parameters, like what you see here, the P vector, is known because these are all videos of demonstrations, essentially kinesthetic demonstrations from Droid or from Bridge and so on, where the body joints of the robot are annotated. Okay, that's how policies are trained, to take images input and predict body joint trajectories. So these body joints are known. What is not known is the camera placement, okay? So in any case, now our goal is to use this calibration, let's say machinery, to go and calibrate all the data out there and be able to train 3D robot policies with lots and lots of data. Yeah, so this is what happens in the real world. But the thing is, no matter how much time we spent, we cannot really, I mean, it's not scalable to expect humans and robots to really scale up demonstration trajectories. I mean, let alone that, to be honest, I personally really don't like learning from demonstration trajectories. I mean, it's very biologically implausible. Very few times our parents took our hand and really moved it to do something, or our dance teacher moved our legs on something. And this is like, mostly humans learn by watching other people as opposed to being, teleoperated. Yeah, so the question is, what can we do instead of behavioral cloning? So can we use now 3D, not implicitly, not as a feature representation, but as explicit 3D to scale up data in simulation? Can we replicate the real world in the simulation? And there is this big, let's say, distinction between manipulation and locomotion. In manipulation, the best demos come from policies trained with behavioral cloning, here pi 0, while in locomotion, the best demos come from sim to real, reinforcement learning in simulation and sim to real transfer, right? Huge difference here between the two fields. And there is a good reason for that. For locomotion, this robot here is going to go down the hill. There's no hills in simulation. It was just a rigid scene, right? You don't care to represent the world very accurately. While for manipulation, you really need to be super accurate of where the objects are, what's going to happen to the objects if I move them, and so on. So the question is, can we do in manipulation what people did for locomotion, really scale up the data in simulation? Okay, because we cannot afford essentially teleoperation and behavioral cloning. So one thing that we did here, Yunzhu led a big multi-university effort on building a more general physics engine. And now you say we already have a lot of physics engines. The big idea behind our recent physics engines here we call Genesis, and Chuang may talk more about this later, is how to make it easy to use, how to make it general, really be able to handle lots and lots of different materials, rigid, liquid, gas, deformable, thin shell objects, granular objects, with all the different solvers, coded from scratch in Tai Chi, in GPU parallelizable programming language, with very good performance, thanks to very good coding of the parallelization, especially in piecewise rigid scenes, rendering, and so on and so forth. And you see here the same scene can be taken care by different physics solvers depending on the type of the material. All right. So we have a physics engine now, we have the platform, and the question is, what do we do with it? How can we automatically populate it with scenes and assets and tasks and reward functions to train robots? Because if you have humans coding all these things up, then you're not going to save time. Like what we're trying to do to take the human out of the loop, you won't be able to do it unless you can also automate the data collection in simulation. So we have started an effort on automating everything in that pipeline, from generating of the assets to texturing them to assembling on a scene, designing a task and reward, and of course not only us but multiple people in the field. And for me, a lot of pieces of this pipeline are super exciting. For example, computer vision is very close to 3D-ifying any image or video right now. So there was this big revolution in 2023 with Dream Fusion, where you can take any single image, and make a corresponding 3D neural field or mesh and so on with score distillation sampling. And by using exactly that machinery, we're able to create tons of assets for the scenes we cared about, like food, for example, with carrots, pieces of carrots, beans, and so on and so forth. And then once you make the geometry, then you ask the language model, okay, how big shall I make it, and what physics properties I should put? And the language model knows very well how the carrot should feel, and how the fact that a pumpkin is bigger than a cauliflower, etc., and predicts very plausible physics quantities. And we're not trying to make here twins. We're trying to make distributions, plausible distributions in the simulation that can encompass the real world. We're not trying to find these golden physics properties of the cauliflower. We just want something plausible here. And look at these two excellent papers, Chuang Gan 3D 2.0 and others 2.5, and the CAST paper that takes a scene and makes a bunch of 3D meshes. I mean, this is absolutely wonderful to see. You have the picture of the shoe, and not even score distillation sampling. When I told to you about SDS, that was an optimization process. Now there is no optimization. These are feed-forward networks that take images and spit out, sign distance functions that can be mapped to meshes directly. thanks to very, very, very big data sets like Objaverse with tens of millions of assets where you can learn that mapping from image to mesh. Okay, and so you can use this for your assets. Absolutely, we're not there. There's no way you can learn to tie the shoes with this rigid shoe here. I mean, the laces here are rigidly attached on the shoe. But we totally see a future where agentic systems are going to be looking at images and thinking about, how to build a mesh, where to put the holes on the shoe, how to make the lace, how to pass the lace in the shoe, and so on and so forth. So this is one, line of research that I'm very excited about. And let me quickly talk to you about our tiny contribution here, led by Yuchen Lin on Part Crafter, of how to map images not to one mesh, but rather to a set of meshes for the different parts of an object or the different parts in a scene. So Chuang Gan 3D, as well as other models, have revolutionized the image to 3D with super large scale models of latent diffusion that take 3D point clouds to a latent space, okay? And then they train diffusion process in that latent space. So there is a VAE, so let me show you the VAE here, that takes surface points, what you see here in the upper right, surface points on the point cloud, it encodes those into latent vectors, okay? And then decodes sign distance functions, and from sign distance functions you can build a mesh, okay? Through marching cubes. So we have built those VAEs, and what this TriPoSG does, essentially trains a diffusion model on that latent space within incredible amount of data. There are 4 billion parameter model, really, really large scale to map images, image prompts to essentially, to denoise essentially, to denoise essentially the latent 3D point cloud features. And then once you denoise the tokens, the decoder of the VAE essentially will map them into a sign distance function and you get the mesh. So this happens in a monolithic object, but can we go to part-based? Can we go in a part-based? And what we did is the following. We saw that in Objaverse, there are annotations for parts that people throw away. And then we said, what if we use those annotations? And what if we make a compositional latent space? Instead of just having one set of latents for the whole object, we have multiple sets of latents where each set of latents takes care of one part. So the purple set of latents take care of the purple part, and the orange set of latents take care of the orange part. And then we replicate the VAE across the parts, right? And we're not even fine-tuning the VAE. The VAE that was trained for objects can work really well for parts as well. And now in that latent diffusion, instead of denoising the latents of one object, we denoise jointly the latents of all the parts by alternating between self-attention within part and cross-attention across parts. So essentially, we start with all the weights of the TriPoSG model. So this is huge because they trained on millions of training samples and we trained only on 50,000. So the pre-training is absolutely critical, and how you repurpose the architecture to go from denoising one single object to denoising parts. And of course, the image prompt is also injected into that denoising process through cross attentions. So things look like this. Here's an image, and jointly all the parts are being denoised, as you see here. And you can vary the number of parts that you can ask for. And why I find this super exciting is because all previous models, if they wanted to denoise multiple things in an image, they had to first segment the part. So they segment the part, and then you feed this as a segmentation prompt to your denoising latent mesh. But the problem is, if you have an object, many parts are not going to be even visible in the image. So if you have a car, you're not going to even see the parts. And here you see the bed is very, for example, occluded. Now, this is in the scene level. Now, if you go to an object level, things are even worse. Here, for example, you don't even see the parts. So this segmentation prompted methods could not actually even be used. We have as a baseline this hollow part that first makes a whole mesh and then segments that mesh and so on. And our model just does the whole thing immediately at one shot. So you see, we have an image, we predict batch of parts by cross attention to the image. I think this is very cute. Like we use the image as a prompt into that 3D generation process. Okay, not like as a very strong guidance, like, using pixel-aligned Gaussians and so on, because so many things are missing from the image, right? So many things in the scene are just not there. Okay, so Now, what about that? So we have assets, and we have physics from, the LLMs. And then now we need to set tasks and reward functions and so on. And how we're going to do that? We're going to translate videos to simulations. We can take a whole video and make a corresponding simulation by making a real-to-sim pipeline of, detecting the objects and segmenting them and 3D reconstructing them with the machinery that I just told you. And this is precisely what we did in this work robot arena, which we're going to present on the 25th, on the workshop in the 25th. And the purpose of robot arena is to automate evaluation of robot manipulation policies in simulation. Okay, really scale up the evaluation environments and tasks by translating automatically without any human involvement a video to a corresponding simulation evaluation environment. Okay, so what happens essentially is you take the video, you make a corresponding simulation environment by segmenting the objects and 3D reconstructing them, place them in the right place, as well as you create perturbations on that simulation environment, and then you automate even the scoring and evaluation using vision language models and some techniques we'll discuss in a few days if you want to join that workshop. Great, and this brings us to the main topic, which is world models. How many minutes I have? 5. 2, 3, okay, not that much. Okay, so world models, maybe I want to very quickly to say that world models, we have video generative models that generate the future of the scene in pixel space, okay? And all the time they hallucinate, and also they're very slow. That's the other problem. Although, I truly love them, and, I think the revolution are going to come soon from that direction. But if we look at game engines, they can also generate beautiful videos, but they don't generate pixels directly. What they do is they have entities and they just move them around, and they also move the camera around, and then they render. So they predict in this much structured space. So motion is very important, right? And there is explicitly this constraint of permanence of entities over time. So the question is, can we also do the same thing? Can we predict in this structured way? That was the topic of the workshop, structured world models. So the structure is essentially the motion, the 3D scene and motion. That's one way to understand the structure. That's one way. I'm sure there are multiple ways. So point trajectories are robot subgoals. There has been many recent papers that use point tracks in a video to represent goals for robot policies. Not just tasks, but rather fine-grained motion tracks. And I want to mention that this work of point trajectory started with my student here, Adam Harley, from his work PIPS, where it was the first work that says, don't chain optical flow fields over time, rather than take multiple frames together and predicts trajectories directly through an iterative refinement process. And recently we have a paper here led by Adam, All Tracker, that really pushes again, PIPS is his first paper that started this multi-frame trajectory, and All Tracker, it has the fastest and most high quality point tracks for you guys to use. If as the sub-goals on your policies, you see here, every point on the video is tracked in different resolutions. And also we have a recent work with 3D point trajectories where the tracking happens directly in 3D in a persistent space where camera pose is taken into account, and camera pose comes from Duster or some other fantastic, 3D extraction ideas from videos. And this is the very last part of the talk, neural simulators. So can we, much like a physics engine, instead of using Newton's Newton's solver to find the solution to these equations of motion, can we instead learn those equations of motion? Can we build neural models that condition on the initial configuration of a point cloud and then action of the robot predict where the points are going to go? And you see, you generate a video, you move the points around, you color them, and you render, and you have a video. And we'll have 2 versions of this. The version 1 is you condition on the actions, and the version 2 is you don't condition on the actions, you actually predict the joint action and object motion trajectory distribution. So we predict the distribution of both actions and objects. And we have this architecture that very much is borrowed from video generation models, where instead of predicting pixels, it actually predicts motion trajectories, and it's a diffusion model. You take motion trajectories, you add noise, you predict back the noise, and because there are too many points on your point cloud, essentially you have this set of latents, much like a perceiver. For those that know the paper, set of latents here. and the attentions are between the point features and latents. And you created, how do you learn that point trajectory? It's very difficult to get 3D point ground truth from videos, so you can collect them from simulators. And then, you can test how well this model does. And, it does pretty well. And it does much better than graph neural networks that used to be deterministic. There are many, many papers that try to predict 3D trajectories of particles with graph neural networks. But because we have a generative approach, we're able to do very well for long-term prediction. And we fire this object essentially recurrently over time. And this is the last kind of, unfortunately, we don't have that many results to back this up, but this is what I'm most excited about, is that when you model both the distribution over motion of your object particles and actions, then you can do more predictive control, not with the classical way and by searching over action trajectories and so on and optimization, but rather through guiding that diffusion model. You can set states and goal states in your object, and through guidance infer the actions that will get you there. Because this is the standard thing that do for model-based reinforcement learning and has not worked so far. The action optimization essentially will exploit mistakes of your dynamics model. So what if we see this completely differently? Let's build trajectory generative models and guide them. And this is the way to infer the actions that achieve corresponding goals through essentially differentiable constraints and rewards. And this is something that we're the first to try this out by encoding the state as object particles and so on. So the takeaways as 3D reasoning for robot manipulation. Computer vision is taking care of bringing us from images and videos to simulated scenes. And generative models over 3D particles will try to bring the essentially machine learning analog of physics engines. And thank you very much for your attention.
Thank you, Katerina, for the great talk. I think that in the interest of time, while our next speaker sets up, we can get one quick question. Okay. Let me get there.
Yeah, great work. One question, in all your examples, when you do manipulation, the action doesn't change the world in any significant way. But in the real world, when we do actions, we pull an object, something else falls down, right? So how do you incorporate dynamic changes in the world in your approach?
Yes, so I talked about many approaches. So about the 3D robot manipulation policies, I want to mention that at every time step you take as input the image. So essentially it's a closed loop policy. Like each time you act, the scene changes, you take as input the new scene, and then automatically you adapt. Okay, so it's not that you predict a long trajectory and then you close your eyes. No, even if you predict a long trajectory, you only execute the first action and predict again. For the last part, again, you take into account the world because you model essentially the object trajectories, and the idea is the same. You infer the actions, you execute the first, and again, you guide again and plan again. So it's a closed loop system. Thank you for your question.
Thank you, Katerina. I think that you can ask more questions later. She's around, and she's going to be here also for the panel discussion later. So,
hello. Is that good?
Yeah, perfect. So it's an honor to have Jonathan here with us today. So Jonathan is a research scientist at NVIDIA, and prior to that, he earned his PhD at McGill University. And at NVIDIA, he works on many things. He's passionate about computer vision, synthetic data generation, and reinforcement learning, and he spent quite some time on leveraging synthetic data for object detection, pose estimation, and few-shot learning. So please, Jonathan, we are curious to know what was your kid's dream.
Thank you, Alberta. Well, it would be hard to match Katrina's energy. Thank you for the great talk. I wish I was giving that talk. It was like all the things I wanted to do, and when I started are like, you're like touching on everything. It's really cool. Do I need to put the microphone on this thing? It's just this, okay, cool. All right, so I came up with the title this week. So building bridges. So let's talk a little bit about, about me. So I'm from La Belle Province de Quebec, a very cold place. I came from the land of ice and sea. So it's really cold, and I'm from a small town, and this is going somewhere. So this is the town I'm from. It's called Château-Zdal, the blue star. And then there's nothing around there. There's just like emptiness. It's like nothing north, south, east, west. It's just like anywhere. But we wanted to go to Quebec City because that's the biggest city that's the closest, about 5 hours, 6 hours drive. And then you would think like there's a direct line from the two cities, right? Like kind of following the river. But no, you kind of go around, because if you zoom in that little location called Tadoussac, there is a big river. And the big river, in order to cross it, you would need to use a boat. And then my dad is a builder, right? And he's like, I don't like that. This is taking forever, especially in the summer. Like there might be a lot of traffic and there's only one boat and you have to wait like a couple hours, so you go around. And my dad was like, I would love to build a bridge, right? I want to build a bridge. And then as I'm growing up, I'm thinking about building bridges and I want to be a builder. But then I ended up doing computer science. I'm not like this like very strong person building like physical things. And then I saw this, I don't know Gendentra, so I'm just going to use whatever he said because it really got me in heart. You agree with Gendentra? Yes. Well, interesting. We'll talk about it. This is kind of like the robotics is far too important to be left to roboticists. So it got me thinking, am I insulted, right? Am I roboticist? Like, am I not good enough for Gendentra? But also I do other things than robotics, right? I do computer vision, right? Like robotics and computer vision. And then they're two different worlds. When I go to a robotics conference, I show really cool videos of my robot doing amazing things and all the great ideas that I have in the physical world. And then I go to a computer vision conference and then I show a table. And then my stats are very good because like my averages are better than your averages. And that's all that matters in the end. All right, there's a big gap between these two cultures, right? And what if I was actually building a bridge between these two places, right? That's my dream, right? So let's look at some statistics, right? So this is me this week, vibe coding. So I downloaded all the abstracts from CVPR from 2015 to 2025. And then I looked at the word counts for robots, robotics, embodied, right? And then as you can see, there's kind of a trend going up, and the y-axis is the percentage, right? I started working at NVIDIA in 2016. See, I think I'm the reason why the robotics has been more and more welcome at CVPR, right? What is it? Oh, Alberta, I think, is saying that correlation doesn't equal causation, right? But does it? I don't know. Maybe. So how did I have that influence over the space of CVPR? But like, I'm kidding. I'm a bridge builder. I want to bridge the gap between NLP and robotics. I want to crossing the bridge between computer vision and robotics, and then laying out the bridge between the agentics and robotics. So these are the kind of three topics I want to talk about. So let's look at kind of LLM. So this is the work ProgProm was a 2022. We're very lucky in our timing that we were working on this just before ChatGPT, like a couple months, and it came out like I think a week or two before ChatGPT, and then it really skyrocketed the experiments of like doing robotics and LLM at the same time. So on this slide, like you have a task, and then on the left-hand side, you're saying like, okay, here's the sort of API to the simulator. Here are the state of the simulator, what is in the world of the simulator. Here's an example of how you're gonna write some code, and here's your task. Like, I want you to cook salmon in the microwave because that's the kind of person you are. Then the LLM is gonna generate the plan. It's gonna do a prompt, and then we'll do some analysis on the code. If it works, it doesn't work, and then eventually you're running it, and then it works. But this is kind of fun, but really I want to have it running on the robot, right? So for state acquisition, we use VILD, which is you put a bunch of words and then it finds segmentations based on the words. And then after that, we can do some motion planning. This doesn't sound very well connected from the perspective of the LLM and the vision or what we're seeing, right? So there's a kind of, they're not they're not as expressive of each other. So how can we solve that problem? So this was our work at CVPR this year, RoboSpatial. So in thinking about sort of leveraging VLMs to do some robotics experiments, we're looking at the capabilities of VLMs in the real world, right? You want to be pointing at some objects, you want to figure out some relationships between objects, right? And then what we found out is they're really bad at like anything for reasoning. At least last summer they were. This year is a little different. So we started this we wanted to understand a little bit more about how to train these models and generate data. All right, so there's different things we're interested in: spatial context, capabilities, configuration. We'll talk a little bit about this. But first of all, in using 3D, there's all these reference frames that are important, and it makes a difference, right? So egocentric. So if I'm looking at something that doesn't really have a reference frame, then in front of me, right, so the footstep on the left, like as I'm moving around, the footstep on the left its front is always going to be defined by my point of view. But then the guitar, if I sit in front of the guitar, as the guitar, I'm moving around it, the front doesn't really change. But if the guitar changes, stop playing. If the guitar changes its orientation, then the front of the guitar changes. And then there's a world coordinates, regardless of what happens in the world coordinates always stays the same. I move, objects move, nothing really changes. So with that in mind, can we build a data set with that information? So what we use is we took 3D bounding boxes, we put them in a 2D map here at the bottom left, and then from there we were able to do some reasoning using heuristics to figure out like what is left, right, and front, right. We could move these bounding boxes as well. Is the bin and left of the cabinet? Yes. So this is our spatial configuration question. There's a context, right? So the point, the vacant space in front of the cabinet. So these are pixel coordinates. And capability, can you move something somewhere else and make it work? And I'm very happy to say that our averages are better than their averages. So if you train our model on, this is a CVPR paper, right? If you train our model, if you train a model on our data and you test it on the spatial reasoning data sets like Blink or Spatial Bench, then our model does better than if you didn't train with our data set. But really, the ultimate goal of all of this is to run it on a robot, right? So here it is, working on a robot. But there's still some like little bits here that you need. You need a system to figure out, like go grasping an object, right? So you point on an object, and then the robot, we have a system that figures out where the object is, a grasping point comes down, picks it up, and then puts it into a pick and place system. Well, this is very exciting, but now I have another problem. I can't have, the system is not, it's hard to compare the system to another system, or at least like from a robotics perspective, right? So can we leverage simulation? This is kind of echoing what Katerina has been doing. Can I use a simulation to help us like kind of like benchmark all of these things? And then, for example, if I give you the scene and I say, pick the fruits in the bowl and the rest in the container, like you could go crazy. You could be like, oh yeah, I'm gonna take the image, I'll take Sam, I'll segment everything, I'll take all of the objects, and then I'm gonna send them to another VLM, and that's gonna give me the description, I'm gonna find all of the objects in the scene, then I'm gonna have this beautiful scene graph, and then I'm gonna take that scene graph with a prompt, and I'll do like a prog prompt type of thing, LLM, robocode, virtual, blah, and then it sends on the robot, then it works, and like you're like, this is so cool, it works, and I'm so happy. Write a paper, send it to a conference, and then, oh, what about a VLA? You didn't compare with a VLA. This doesn't, I'm like, oh, but it works, and it's so great. They can do things that I've never seen. But yeah, a VLA. Have you seen the data set size for JCO robot, like a Kinova Gen 3? And then is your argument that a VLA is going to solve these tasks? I don't know. So instead of being very frustrated about my reviews, I was thinking like, okay, maybe I can figure this out in a better way, right? I can sort of understand comparisons in a way that we could like, it would be a little better. All right, so if I render here, this is like what we're currently working on. I think that we're presenting this work at another workshop with Jenny is gonna be doing it on, I think it's Wednesday. So if I give you a render image from before a task and then a sim API, then we're going to define an interface for you, and then you can use your system, and then after that, send it to the robot. But also at the top part could be a VLA interface, right? So you could have a benchmark for either if you're building a system with computer vision and motion planning, or you could have a VLA kind of. This is very exciting. Now you'll be able to compare any systems to a VLA. And then it's going to make my life a lot easier. All right. So some of what we're looking at is like a full scene state, a little bit what we did for ProgProm, right? No visual perception required. So if you want to do a pure kind of coding agent, you are going to have also annotated rendering scenes. So some VLM system, they use segmentation on the objects, or like they'll have a scene with a bunch of like segmentations, and then or letters, and they'll say A, B, A, C, D. I think S3 is kind of my favorite. It's like you just render the scene, there's just depth, and then from there you go, right? And then the 3D point cloud, I think there's really cool work on VLM point clouds, but they're not very well explored in terms of their applications in robotics, which now I'm making a bold statement, but I would like to see more of the kind of the 3D stuff being applied to robotics in the context. And then what I've discussions I've had with computer vision people are very interesting, because they are not really thinking about the problems of robotics. They feel like it's as accessible as computer vision, right? So in computer vision, I made the joke about the averages and foreshadowing this. When you're doing averages, it's really cool, but if you have like 2 errors over there, it doesn't really change the average all that much. Maybe it even improves it, and then you're very happy. But in robotics, if you're building on a system or anything, and there's like a small error, the error can just like turn your robot to fail at its task, right? And that creates a lot of difficulties in terms of measuring and accepting the reality of doing robotics. And it always shocks the computer vision people when they come into our lab and then we show them robotics experiments, and they're like, oh my God, this is so difficult. Like, why do you need 5 monitors, and why do you need like 13 terminals open, right? So I'm very excited to like think about to go back to this and about building bridges. All right, so this, so I did some research, right? So this is robotics is far too important to be left to roboticists. Actually, it comes from La guerre, c'est une chose trop grave pour la confier à des militaires, which is translated, war is too important to be left to the generals. Georges Clemenceau, it's a very old. So thinking about it, I'm like, this is grounded in the idea that society together, we have to build things, right? And I feel like us roboticists are the generals, right? Like we're right there, we're leading the charge. But what's important is for us to, with everyone else, is to build bridges, to improve our relationships with these communities, and also make the work accessible to them. So their improvements on their algorithms improves our robotics, and then the improvements on our robotics systems improves their algorithms on their side. And hopefully we get to experience that. Yeah, I'd like to thank many of my collaborators. This is just a small subset. Yeah, thank you so much. Also, as you're thinking of a question, I feel like feet are underrepresented at CVPR, as you can see here. Body, eye, hand, head, all like have a pretty good percentage of papers, but feet, like really, very low.
Wow, thank you, Jonathan, for the very inspiring talk.
Thank you, Albert.
It was very insightful, but also fun. So again, while our next speaker sets up, let's open the floor to 1 or 2 questions from the audience. Does anyone have any question? Okay, maybe I have one. So as you discussed a lot, like building bridges. So how did you do that? Or what do you think is the best way to build in these bridges? Because I agree very much with you that these two communities, if they cooperate, they could lead like to amazing things, but we really speak a different language. So what's your take on
we see it a lot in the robotics community, trying to do more like the computer vision communities. Like tables are becoming, I've seen it, tables are becoming more and more and more important. Like your averages have to be better than my averages. I think it's one way. You change your way to be more like someone else. So now these people have your respect, right? They look at your papers and it's more, oh, okay, it looks more like my paper. And then it's one way. I think providing interfaces, like an interface to the problem, because the computer vision community, they're very interested in robotics. Like there's a lot of like, I was at CVPR last week. A lot of people are like really into it. But how to get into it is very difficult for them, right? Because a real robot is very hard even to start with. But it would be interesting to have, like, I'm thinking the simulation or the simulated kind of benchmark that we're trying to work on towards is a place that we could start building. And then this is so far my way of trying to like bridge that gap, but it's difficult.
Yeah, definitely. Then looking forward to see how that develops. Okay, well, let's thanks once again, Jonathan.
Thank you so much, guys.
So our next speaker is Chuang Gan. Chuang is a faculty member at the UMass Ambrus, and he's also a research manager at the MIT IBM Watson AI Lab. And his research really pushes human-like capabilities of autonomous agents towards reasoning and acting in the physical world. And he also contributed to the Genesis simulator that previously Katerina mentioned. And he graduated with honors from Yunzhu University. And he spent some time as a postdoctoral researcher at MIT. So please, Chuang, the floor is yours.
All right. So thanks for the next introduction. So I'm very excited to be invited to this world model workshop. So today, actually, I will present a recent release stuff. So it actually is a combination of the long-term effort we have been working on called the world simulator. So how many people have seen this actually just posted yesterday? Virtual community, raise your hand. Okay, a little bit. Okay, that's good. So which means that you can learn that from my talk. All right, so let's start to let's start a talk to watch a video of my daughter Katerina. So she's playing a popular game called Circle Puzzle. We could find that she has a basic knowledge about objects and how to interact them. And eventually, she's managed to figure out a plan to finish the task very efficiently. Even though she sometimes to reformulate the plan, but eventually she can make it in a very efficient way. So the question is that why could she succeed in this task? The cognitive study from cognitive science has tried that even the 15-year-old baby here has the knowledge about object, and also the abstract knowledge about object affordance, how to interact with them. And eventually, she can use her mental model to imagine what's going to happen next and plan her action accordingly. Then the most question in our lab have been started, how about the embodied intelligence today, that how we can reach the level of the Katerina. Then the first question we need to answer is that whether the most advanced embodied intelligent agent has this kind of level flexibility of my daughter Katerina or not. So you might say yes, because we have seen many powerful robots that for them they can help you to unfold clothes, play soccer, help you to clean the room, and even do this kind of fancy treasure and kite game. But I would still say that we don't really have the kind of general embodied agent. So what do I mean by that one? To start with, maybe we can have a rough definition of a general agent. The definition can be very different, but usually we talk about a robot agent that can take multi-modal instruction and perform a wide range of tasks across diverse environments. And then we can see that how about the most, actually last year, one of the most advanced robot systems. For example, this robot Aloha can perform that kind of task in terms of generalization. Because even though they are very powerful in many perspectives, but they are still fail in some easy tasks that actually are trivial for humans. So from this video, we can say that we are still far from having that kind of generally embodied agents that can interact with the world as flexible as we human. So, but in our lab, we are trying to do that is trying to take another route that by reverse engineering the world model working in human brain and building a world simulator to achieve the goal. There's many definitions of world model. For them, in this, people have been talking about world knowledges and world model, has thinking about using this kind of large multimodal model to represent it as a world model. They actually can do some decent job here. For example, you ask these images, so you give these images, ask what will happen next. So they basically can tell that, okay, these images show a hand appearing to drop by egg, and without support, the egg will likely fall due to gravity and may break upon hitting the hard surface. It seems that they have the kind of decent understanding about the object and also physics, right? But how about we take a little bit harder question? But this might also be trivial for everyone. So which ball will reach the ground further? So the GPT-4 will answer that they will ground at the same time. But based on our human knowledge, actually we can answer this query very easily because this ball takes a shorter path and has larger acceleration. So apparently this ball will hit the ground earlier, right? And you ask the GPT-4, even he made the wrong mistake, but he can return some fact in a very clear way. For example, he said that there are only false icons of the ball in gravity, which puts them down within the same acceleration. The time it takes for them fall in certain vertical distance is independent of horizontal distance cover, and then they fall at the same time. So all the facts they are tying is really right, but they just not go out with this scenario here. And there's more, more well-known world model simulator. So world simulator definition is using the video model. I think Katerina also talked about this one. They indeed can generate very photorealistic images, but we also know they are not really reliable, that they are making this kind of funny physical mistake. For them in this box learning, they can even translate this them clearly learn from, and also this kind of anti-physics video generation behavior. And even we try to do the very basic manipulation task for them. They can custom task, and then the chair just fly away. So yeah, maybe we have more and more data, the model will become better and better. But still we need to touch the basics that how we can model the kind of physics work in a much more accurate way, right? So in our lab, we have been working on the idea called generative simulation. The idea is to basically combine the power of generative AI and differentiable physics engine. Let's take a simple example as a question that when you see these images, can anyone tell me that which object is heavier? So how many people think the green sphere is heavier? Raise your hand. How many people think the green sphere? Okay. Now if you raise your hand, it's very confusing, right? But how about I see this video? Okay, tell me, so how many people think the green sphere is heavier? Okay, how do you answer the question? You're basing some physics knowledge of conservation of momentum, right? So the idea of using physics simulation to do that kind of reverse physics is really similar to how we humans solve the problem. So we have building that kind of tool called the differentiable simulation for a while. So the basic idea that given the current state of physical parameter, and then for physics simulation, actually you can do the forward path, and then you can control the whole physical process. And in this case, actually, you can, so the idea here, we're trying to using a physics simulator to estimate the field parameter is that you're trying to simulate the object trajectory and trying to see whether you simulate trajectory matching the video result. If they can match, actually means that you estimate the field parameter in an accurate way, right? So the objective function here, you can just minimize the loss by inferring the optimal physical parameter. So this is the reason why we needed to build a differentiable physics simulator. So the idea here, we're trying to make the phase equation differentiable, and then you can solve this inverse phase problem by by using gradient descent. It's very similar to you training your neural network. And here example that you take a left-side real-world example, and we can using the kind of different phase engineer to reconstruct the phase parameter and build the conditional twin in a very accurate way. And you may be wondering that how this approach that can generate to much more complex shape. For them, they kind of articulated body and even solid body. So the idea here is, besides the differentiable phase engine, we can add another differentiable rendering engine here. So the idea that we can compare your rendered images and the video observation and to see whether they are matching or not. And then we leveraging the differential phase engine and differentiable rendering okay, so the whole inverse phase problem using gradient descent again. So this is a real example that you can take in, So you can take a real world called router example and reconstruct their control signal in the simulation in an accurate way. And so go beyond that kind of readable, we also think about how we can do that kind of system magnification without any geometry prior. For example, we're trying to estimate the Young's modulus of this code and also the viscosity of this droplet. To achieve that, we combine the idea of a neural rendering, that you take multi-view images, you reconstruct both geometry and the physics. In this way, actually, you can reconstruct the physics of that kind of solid body. So you can reconstruct both geometry and the physics of a solid body in a relatively decent way. So how about this kind of world model really related to the robot manipulation? It's more about the core of this workshop. So the idea here is that this differential phase engine can not only be used for the system magnification, by simply adapt this kind of framework, we can also use that to show the robotic manipulation task. For example, the phase parameter here, we can actually replace with the action. And then with the current system, with the system meter and action, you actually can also control the whole physical process. And since this is a planning task, you can always define a reward function to tell you how well you solve this task, right? And again, the objective then the training objective has to become to maximize the total reward you can earn by choosing an optimal action sequence. Similar to previous solution, you can also using gradient descent to solve that kind of action optimization problem. We first apply this idea to the solid body manipulation task. So the task here is trying to manipulate an effector and deform the plastic to a desired shape. So traditional approach usually using the reinforcement learning to solve this problem, which is actually not very data efficient. In our solution, we propose this kind of gradient-based physics solution. We found that by only using a 200 example, we can optimize a beautiful trajectory in a very flexible way. But for reinforcement learning, even we train for 10K episodes, we are not able to find any feasible solutions. So on the left side, we draw the curve that on the green side, with the green color, you can see that this gradient-based physics solution can earn much more reward than the traditional reinforcement learning algorithm. And you may be curious that how the kind of simulation framework can really generate to the real world, because in the simulation, you always do the kind of open loop trajectory optimization, but in the real world, you're always using the kind of closed loop policy learning. So here, we're always using the kind of neural network so the perspective of using the differential simulator is more like a data engine. We're trying to provide a large and diverse set of downstream data, and then we can using that kind of training the foundation model or whatever the policy model you really want. So we have applied this kind of powerful idea for many different applications. For example, here is the project we done 2 or 3 years ago. So the task here we're trying to do the kind of multi-material cutting task. Basically, we aim to cut as much volume as possible, but to avoid to hitting the middle rigid body curve. And we're using different phase engine to optimize the beautiful trajectory here. And then we learning this kind of closed loop policy, and so that they can actually transfer well in the real world task, that they can cut different sides of the kind of route without colliding with the rigid curve in the middle. And Katerina's student has also intended this idea. It's Shenzhou, so he has intended this idea to do the kind of fluid manipulation and transfer to teach robot to make this kind of ice cream and make coffee latte for you. And my student Ian has even intended that kind of framework to do the kind of thin shell contact-rich manipulation, and also the kind of self-tearing locomotion task and also manipulation task. But this program actually has several problems to really scale up. The first problem that you can see that most of the robot simulation is more like one simulator for one material. We are not really exist that kind of simulator can unify all the effort from rigid body, articulated, solid body, deformable, all the things together. And the second part, even you have a very powerful simulator, you still need to spend tremendous time to figure out what task you want to do. For example, in the behavior, we need to define 1,000 human daily life. And also we need to set up the scene manually. And then we need to humanly writing the kind of reward function to make it learn. So the idea here that is that we're trying to build the kind of generative and unified field simulation. This is the original of the Genesis simulator you met already here. So the idea is that how we build a kind of unified simulator. So this Genesis simulator has came out since last September. I think by yesterday, it reached around 100K. It just reached 100K download. So the idea of Genesis is that it supports a large diverse set of object material, including rigid body, liquid, gas material, deformable, thin shell, and granular. So one of the most important is called unified simulator, because that is that we implemented them into one unified framework and also solve most of their coupling, material coupling problem. Then, which means that you don't really need to shift the simulator at some time, that you can just use Genesis for all the tasks. And we also support a wide range of robots, from robots that are mobile manipulation, like a robot, drones, soft robots. So everything actually you can do. So everything you want to do about robot, we also can always achieve that in the Genesis world. And since the last release, actually, it received big attention. If you haven't downloaded that, okay, try to go to the website and make a try. Even we have this in Genesis there, we still need to solve a second question, that how we can enable that kind of automated skill learning in the simulation. This is the essential how we really can scale up the simulation learning, because many robot people will argue whether the simulation can be useful or not, because they can always teleoperation data that can be much fast to get in policy. But here, but when you're setting a simulation, you need to learn. You also need to actually finding aside the proposed tasks, and also trying to find out the right signal to training the framework. Okay, this seems a little bit tedious. And our idea is that how can we automate the whole process? So this is the essential idea of RobotGen. We have been released, I think, 1.5 years ago. So the idea here is that we're trying to using the generative model that can automate proposed tasks, doing the scene generation, as well as generating the training, as well as writing the reward function, objective function, or even select the training algorithm. And then everything actually can be automated learning simulation with little human intervention. So let's take an example that we gave this kind of arm and the object safe. We can actually ask a larger model, okay, what can you do with this robot and this safe? He actually gave an answer that you can actually open the safe door, or you can retrieve one gold bar and lock the safe. So based on this kind of language description, we can then generate the scene. So basically, you can we can retrieve the relevant eyesight from almost 3 library and define the eyesight size based on the knowledge in the larger model or world model, and then we can define the scene configuration and also how we put the scene. For our asset, we can either using the existing asset, or we can using some type of 3D model to achieve that one. And another perspective we find very important is doing this kind of idea of test time scaling. So basically, you're using a verifier to verify. So basically, generate a bunch of different scenes. You're using VLM as a verifier to verify to select which scene actually can be best valid for a task. With all this scene population, the last step is trying to do the skill learning. And this is a principal power for always for human, okay, whether we're using task motion planning, how we can decompose the task, or even we can training how we can design the reward function. But this part actually can be always automated using the generative model. For example, we can use LM to write a reward function. We can use LM to decompose tasks. And later, I will also tell you how we can, in some challenging tasks, how we can use a video model to define the goal and the reward function and enable all the robot skill learning automatically in the simulation. This is our mission. As a result, that we have making that kind of so that kind of automated skill that basically robot give a task that all the robot skill learning can be automatically happen in the simulation. You can find using that time we can learning a large range of diverse skills, including locomotion, manipulation, desert manipulation, mobile manipulation. So everything happens is automated in the simulation. So essentially, when we talk about the agent everywhere, actually what we hope to get, we have a kind of generative robotic agent that can automatically propose new tasks. Teach them have no skill, and all the process should be endless and automated. And in this framework, actually, we found two challenging for the next step. First, that for writing the training signal, people are always using the kind of LM. Actually, LM don't really have too much information for them to try the solve body material. So it's usually hard to generate the goal for deformed object. And also, we finding that the robot body is also, in sometimes also limitation that, for example, in some manipulation tasks, the robot greater might not be enough to solve all the tasks. And to solve the first problem in our recent work that we called the Lucy bot, the idea that we're trying to using a video model to do the goal generation, for example, given the task. So we're trying to learning from this kind of generated video, for example, how human pouring the water, how human actually pick up a spoon and go a sponsor stand, or even pick up the knife and cut the dust. And using the video, actually, we can actually taking the video and training a perception model to basically guiding the trajectory, and then we're using some optimization. So basically, we take the human initial so we take the human trajectory as the initial trajectory for robot policy, and then we can refine the policy using the differential physics engine. So this is the high-level idea. So as a result, we are able to teach robot to a bunch of very diverse, deformable object manipulation tasks. And now, actually, we learn we get the training signal from generated video. And the second part, actually, we also think that for robot manipulation tasks, that for the human so many tasks, that you need to have some tool here. And the last effort actually is also human-defined tool. And our idea that whether we can use the kind of generative simulation idea, can using LM, basically they can for them give a user what task they want to. So we basically can use LM to generate the tool. And then you have another VRM doing the multi-agent system. They can evaluate the thing whether the tool can solve the task or not. Then you can revise the tool size. And eventually you can do job optimization of the kind of tool design as well as the policy learning. Here I want to show some real world results. For example, here we are designing that here actually we want to pouring the water into this small size of the bottle. Actually, if you just put in the bottle here, it's very hard. But we design that kind of tool here that the robot can do the task in a much flexible and easy way. And we also taking this, we also making that kind of pizza example that we're trying to make a tool that how we can put in salt in this kind of small pool and making the pizza for you. All right, so in the second part of the talk, actually, we mostly talk about our mission that how many people has watched the video of death rates become human? Raise your hand. Okay, not that much. So basically, I'm telling a story how human and robot can co-evolve in the social world. So as we all know that the robot will be everywhere in the next few years. And the embodied intelligence should not only about interact with the physical world, because the most important perspective in the world actually is human. So in the next year, we have been thinking about the following problem that when robots become everywhere today, how we can deal with because they probably will share the same community with us. We need to figure out how robots can intelligently cooperate and even sometimes they compete. And how humans develop kind of social relationship and build communities with agents. And most importantly, fundamentally, how we can deal with them that both coexist in our open world. So this goal actually we call as embodied physical and social intelligence. We need to build a robot that can interact with physical world, but as well as with other intelligent beings. This is called embodied physical and social intelligence. And to achieve that goal, actually we need a unified world simulator that can support the simulation of robot, human, and also their communities. How can we be there? So this is the essential idea. So this is the essential motivation for our virtual community project. So this virtual community is really about an open world for robots, human, and society, how they can collaborate, coevolve, and grow together. So basically, the virtual community built on top of Genesis, which means that they inherit most of the robot simulation capabilities from Genesis. But we make two innovations here. That the first part, we're trying to building a unified simulation for both human and robot. So this is this actually makes Genesis to be an optimal choice for us. So you probably have seen a lot of that kind of human interact, so human avatar example, but we have to say most of them actually building on the game engine for the Unity or even Unreal. The problem of this one, they are not really designed for robotics. So that's why we take a reverse path. That instead of building a Unity and Unreal, actually we build from a robot simulator, and then we add human and robot interaction on top of them. So this is the right direction we choose. And another idea that we think most of our robot learning right now is really happen in either in our environment or in some the kind of game human created environment. But actually, we really need the robot and human coexist in the real world scenario. All the study really need to get in the real world geometry data. So this is a big effort we have trying to reproduce the world anywhere. So basically, we can take the Google Map, select the location, coordinate, altitude, and we can using the Google View images and also the 3D tile data, basically trying to reconstruct the world everywhere. And then we populate the agent and building a bunch of tasks in the real world scenario. So this is the real mission of virtual community. Scale up robot and human learning in real world scenario. And as a result, that we can generate that can. So basically, we can take we can take anywhere in the world, give us the city. Actually, we can reconstruct the city scenario here, and then we can populate agent based on this kind of generate this thing. So actually, we leveraging this kind of 3D and 2D data as well as the map data. And we start from the 3D pile data, the Google pile data, but it's well known it's not really that kind of simulation ready to use. It's not that kind of clean, and also their mesh geometry not correct. So we actually propose that kind of geometry simplification of the building, and then we doing the kind of perception masking some noisy actor using perception model to detect some object, for example, the car, the vehicle, human, and remove them out. We also using the generative model such as stable diffusion to implement the texture. To basically to generate the kind of relatively photorealistic real-world scene at scale. And then that part, we actually building the kind of scene-grounded agents that basically we also have the kind of well-known character, LM mask, all the people here based on we use LM to design their profile, and then we think about how they will interact with the agent. And eventually, we are building that kind of large-scale physical and social interaction happen in real world, including a political campaign, the kind of a robot following the child, or even the kind of offensive or assaulting task. And also it's happening everywhere in the world, from London, New York, Park, so we can always simulate the real world scene and define activity beyond here. All right, so I'm going to summarize my talk. So I've been asking that what's the long-term vision of the Genesis stuff. So basically, we're always thinking that the Genesis could be considered the next generation of the linear kernel for embodied AI. And we see there will be a large, so there will be two-step effort we are trying to working on. So the first thing we call is called Genesis build. Essentially, it's a large-scale synthetic robotic data generation pipeline. We are working on releasing a super large robot manipulation demonstration data set and also evaluate benchmark that is for all the robot community can training foundation model as well as doing the model evaluation in simulation at scale. On the second part, we are working on building the kind of undivided 3D embodied foundation model. So basically, we're thinking that a lot of robot poly learning right now happen on the 2D. It's obvious that in many cases, even as Katerina will show you, that a lot of things working on 3D or even 4D can be much simpler and the poly can be much easier to generalize. But the problem is that we don't really have data. And Genesis provides a kind of simulator actually is all the 3D 4D data came as free. So this actually offers us an opportunity to build in the kind of 3D-based or 4D-based embodied world foundation model. And we are also thinking that to connect with the foundation model with symbolic and feed engine. So the idea that you have already seen some idea about using language to control the physics engine in the Genesis demo. So basically, we are thinking to building another cursor version of the physics engine. So basically, the ultimate goal that we're trying to remove the barrier for people using the physics simulation. We hope everyone can just use their language, can simulate the scene. So basically, it's more like using the chat GPT. You put your query, it can edit the scene, and generating a site, generate the training signal, everything that you can use in language to interact with Genesis to achieve robot learning at scale. All right, so this is all my talk. I'm happy to take any question. Thank you.
Okay, thank you, Chuang. Again, while the next speaker sets up, do you have any question to ask? And thank you for the great presentation, by the way. Coming.
Thanks for the talk. I'm curious how you decided on choosing the Genesis simulator and what's your experience using other simulators and what's your decision process for that?
Okay, so the question is that how can we compare with the Genesis and other simulation? Is my understanding correct?
Or more so about how you decided on choosing Genesis and your specific requirements in making that decision.
Okay. So let me share a little bit story about building my roadmap to building the world simulator. So how many people had heard of a simulator called 3D World? Raise your hand. Not that much, okay. Okay, this is actually the first simulator I have built since 2017, when I was the first day at 2018. The first day I'm being a postdoc at MIT. So the idea of 3D World is building, actually at that time, a lot of robot simulator building on top of the Unity of the kind of game engine. So the idea that we really want to have, so because before people most using the kind of robot simulator, it's really about physics, not really about the photorealistic rendering. And from computer vision community, people are always thinking that we need both good physics and also good rendering quality. So this is essentially Unity and Unreal, this kind of game engine become an automatic choice to do that one because they basically couple of good. So basic game engine very aligned with the purpose of this kind of robot simulator that you can have good physics and good rendering. I have been working on the 3D World. So this is essentially how we build in 3D World and also some habitat, virtual community, or even the Sapien all built on this idea. But we have been working on this kind of 3 or 4 years that we never get it popular and be very easy to use. One of the reasons that the kind of Unity and Unreal is most designed for game, not for robotics. And a lot of time, actually, we spend time is mostly on fixing bugs on Unity and Unreal. And people, and also you probably Unity and Unreal, actually, they are not using Python. That's the most popular language to write. So you have to go into the low level to keep debugging. This idea that we're thinking, okay, why? And also, Unreal field is not really doing for anything about robot. It's not easy to put a robot body in the simulator at all. At that time, we are thinking, okay, we have to build something from scratch. And that time, I think like 2021, 22, I don't remember exactly. And Yuan Ming actually told me, okay, I'm building a compiler called Tai Chi. And he's most from cryptography community, and he writes the last paper at MIT with me is actually the pricing lab. We see the opportunity that we can use in the kind of differentiable simulator, the kind of programming to really write so that kind of robot simulator from scratch. And then the story that I met Xianzhou, actually Katerina's student, he's willing to take the lead and actually to build a kind of unified Genesis simulator from scratch with full control, and the most important thing, makes it fully open source. So I can see this is more like a cycle that is more like, for example, DeepSeek essentially put all the language model trained to be open source, and Genesis also want to do the same. If you're using the SLG or some other, you probably see that a lot of simulators are not really open source in there. Even Matterworth, SFG, they are not really open in the low level, but the Genesis actually open everything. Essentially, I think I hear that last week, SFG also decided to open everything, so this actually a good cycle for everything. So I honestly don't know who will be the winner, and also I don't think we need to know who is the winner, but the thing that we really need to build this kind of ecosystem to push robot simulation can be widely used. Everyone can contribute, and also every can be easy to use. This is my mission. All right.
Let's thank again our speaker then. So our next speaker is Yunzhu Li. Yunzhu is a assistant professor at Columbia University, and his work tries to end the robot with the capability of perceiving and interacting with the physical world, and it tries to do that leveraging structured world models and multimodal perception. Prior joining Columbia, he was an assistant professor of University of Illinois Urbana-Champaign. And he also spent some time as a postdoc at Stanford, and he obtained his PhD at MIT, advised by Rusty Drake and Antonio Torralba. So, Yunzhu, the floor is yours.
Okay, thank you, Alberta, for the very kind introductions, and super excited to be here. Talking about a series of work we have been doing on trying to simulating and manipulating deformable objects, especially with structured world models. So the first half of the talk will be actually a review of some of the things we have been doing over the years, especially using graph neural network on modeling the dynamics of deformable objects. And the second half of the talk will be about like some of our recent developments on trying to identify the right recipe of modeling and building the digital twins for deformable objects. So specifically, like the key questions we're hoping to answer is, want to arrive at this kind of human level manipulation capabilities. Whereas many of the existing like manipulation systems in the real industrial situations are still like manipulating, for example, boxes. Like you are in academia, you probably have seen many interesting like robotic videos, like robots working with like interesting stuff. But if you ever went to any of this kind of industrial like shows, for example, ProMat or Ultimates, you'll be amazed how many boxes you will see. There's just oceans and oceans of like perfectly shaped boxes where people are moving around. Those are the current reality of what's actually deployed in the industries, which are still very like far away from what we really want the robots to do. For example, humans can do like many like deformable object manipulation tasks at a very high performance, like cracking eggs, bread butter, making bread, making sushi. And one of the key enabling factors is this kind of intuitive models of the world. We learn from our interactions and predict how the environment is going to change if we apply a specific action. For example, how the dough will deform and how the onion pieces will move around. And when we, for example, like when we apply our actions, and we can use that predictive capabilities to plan our behavior. So in general, like this framework works like this. You give this world, you have this planner. This planner will take in the observation as input, and internally, we have this intuitive model that predicts the evolution of the systems under some like novel actions. And then we can plan our behaviors based on this predicted outcome. In order to build this kind of predictive models, there are generally like two ways of doing it. The first way, generally, people currently have been thinking about is this what's called like 2D world models, this pixel like conditioned like action condition prediction models. Generally, they map something, the visual observations, into the latent representation and neural dynamics model over that latent space. The nice things about this lines of work is it can learn directly from partial observations and handle systems where the underlying dynamics are uncertain or unknown. We have success stories like Mu-Zeros, like many other examples. And the key issues of these lines of work, it considers the environment as unstructured, and it's very limited in terms of generalizations. So when we're thinking about those or a pile of coffee beans, we're not thinking of them as just one latent vectors. We have some very structured understanding about this relationship between different components within these dynamical systems. So the other way of building these dynamical systems, especially leveraging structures of the environment, is based on our understanding of physics, like F equals ma. This is what Chuang was talking about on using physics-based engines to build the dynamics models. So this is arguably the most compact way of building this dynamic model and has excellent generalization capabilities. We also have many success stories. But the key issues of deploying this type of model in the manipulation domain is that this model requires full state information of the environments. And sometimes full state and parameter estimations of the environments is just very hard or sometimes impossible, like the examples I showed here. So on the left is model learning. On the right would be structures in the model. So my goal is really trying to bridge the gap and get the best of both worlds and trying to learn model from the robot's interactions with the environments and with structures inspired by understanding of physics, by understanding of geometries, and using this learned model for us to do better physical interactions. So let's make the problem a little more specific. Here is the objective function we hope to optimize. It's the objective function defined over the observation y and the action u. So we have to think through three most critical constraints. The first one is perceptions, which essentially maps the observation into some representation z. And then is a dynamics model. So given the current z and actions, want to predict the evolutions of the systems. And then want to derive the action signals conditioned on the current representation z. So if you look at this kind of formulation, you'll realize that the choice of representation z plays a very important role in deciding the overall structures of the systems. It's very important for us to carefully thinking like what type of z should we use and how we can choose the suitable z's that give us the desired levels of generalizations and sample efficiency. So for many of the work we have been doing so far, we use the representation of particles, which essentially describes the whole environment using a bunch of points. Points describing the overall geometries and interaction both within an object and, of course, different objects. So to model the dynamics of this particle systems, we use graph neural network. We call it graph-based neural dynamics models. Essentially, given a graph of 3 nodes and 3 directed edges, our representations of this environment will be the node set V and S set E. And for every edge pointing from B to A, we'll aggregate the information from the sender and the receiver to derive the representation on that edge, E. And then for all the nodes, we will aggregate all the representation on edges where node A is the receiver. So we'll update the representations on the node A. Then we can define all the objective functions based on the either edge representations or the node representations to do the supervision. Here, what we care is about the evolution of the system. So we predict the evolutions of the systems by minimizing the mean squared error between the predicted next state and the actual next states. Of course, the node encoder is shared among all nodes and edge encoder is shared among all edges. So that's why we choose graph neural networks, because this has some very nice internal structures that allows us to do very simple, efficient learning. So by learning this model, we'll be able to model system. For example, here are examples where 2 fluids fall down and merge with each other. The left is the ground truth. The right is our model's open loop future predictions. Here's another example of mimicking a parallel jaw gripper of deforming class systems. Here's another example of shaking a box of fluids where we control the movement of the container. And our learned dynamics model matches very nicely with what the ground truth shows on the left. And because the node encoder is shared among all nodes and edge encoder is shared among all edges. So the learned model can naturally generalize to systems that are larger than during training, that is 2 times fluid examples. When moving to the real environments, we'll be able to, for example, build some kind of perception systems, do some kind of reconstructions of the objects, can also assign this kind of graph representing the overall structures and overall shape of the environments, both for the rope, for the granular objects, and also for the even for rigid objects. By representing these real objects using graphs, we'll be able to, for them, model their dynamics and even learn the dynamics model directly from the real-world interactions. So in one of our earlier works, we try to tackle this very complicated dumpling making tasks by directly learn the dynamics model from real-world interactions for the elastoplastic object like class systems. And we equip these robotic systems with 15 3D printed tools. and then using like 4 RGB cameras looking at the environments to do the reconstructions of the dough and plan the robot's behaviors within this kind of red regions of interacting with the dough. And the learned systems really benefited from the use of graph-based neural dynamics models. Because of these very nice structures we use, we have shared encoders for both the edges and nodes. So we allow very, very simple, efficient learnings, where for each tool, we only require 20 minutes of real-world interactions, and we can have sufficient data for us to learn pretty decent dynamics models for the modeling of the dynamics of these objects. And this learned dynamics model is noticeably more accurate than the state-of-the-art deformable object simulators like material point methods, even if we apply very extensive system identification. So here is actually the visualizations of the model's predictions and our representations of the environments. Here, the blue points representing the representation of about the geometry of the dough, and red points describing the geometry and our representations of the tool. The first row representing our model's open loop prediction, and second row is the ground truth. You can see our model's prediction closely aligns with what's happened in the real environments. Here's another example of the dynamics of a pusher, another examples of the rollers. We can successfully predict the size and the area of the dough will be enlarged as you apply this kind of rolling operations. And here's actually the actual executions of the robots using this kind of learned dynamics model. So what's interesting about this video is that there will be a person constantly perturbing the robot from doing its job. And the robot has to give the current observations of the environment and reactively and dynamically select what tool to use, which is a decision made at the discrete level. And given that specific tool, the robot has to also decide what specific continuous action to make in order to progress into the next task stage. So this is actually this two-level planning, both at the task level and the motion level, for the robots to be robust to this type of external disturbance. Like I mentioned earlier, the key enabling factor is really this kind of learned dynamics model of this dough that predicts how the shape of the dough will change if you apply a specific actions. And this forward prediction model can allow us to design this kind of predictive, this kind of planning systems that is able to progress over this kind of dumpling making procedure. Here's what's really interesting. After the robots have enough area, the humans cut a circle and humans choose no mercy, destroy everything. And the robot knows it has to start from the very beginning in order to be robust to this kind of external disturbance, which shows the robustness for the robots both within a task stage and across different task stages, and for the robots to actually solve this very complicated long horizon deformable object manipulation task. In the end, the robots will move the dumpling skin on top of this dumpling clip and move this dumpling fillings on the skin and close the dumpling clip in order to make a dumpling. So this, I would say, is a very, very challenging task, especially using this general purpose robot arms equipped with general purpose 3D printed tools. We actually apply this very similar techniques like this neural dynamics model, this graph-based neural dynamics models, also on many other deformable objects. Here is an example of trying to do granular object manipulations. We're still using the same a graph representing the foregrounds of this object piles, and using this graph-based neural dynamics model to predict how the granular pieces will move around if you apply a specific actions. And then we can use this forward model to plan the robot's behavior to rearrange these granular pieces to achieve complicated target configurations. You probably have already realized the target configurations are all the letter shapes from letter A to letter Z. This is a highly non-trivial task because it involves some redistributions of the object masses and also some fine-grained alignments of the object pieces with the targets in order to do this manipulation task. And again, exactly the same framework, this kind of graph-based neural dynamics model can also be applied to multi-object interactions. Here's another example shows you can actually learn this graph dynamics model to predict this multi-object interactions for this kind of stowing task and be able to stow the objects on top of this kind of shelf. So to summarize a little bit of the first half, the take-home message so far is that we use a combination of particles and graph neural networks that is able to model objects dynamics, especially for objects that are compositional and with high degrees of freedom. It handles elastoplastic object, granular media, and also multi-object interactions in the real environment. It comes with two key benefits. The first benefit is about generalizations. Specifically, we can generalize to systems that are even larger than during training, like the fluid examples, or like a target configurations that are never seen during training, like the A, B, C, D, E, F, G, those letter shapes, because the training data are actually just randomly like pushing actions on these object piles. The second key benefit is about sample efficiencies. Like for example, in the dumpling making one, all the models are learned from real-world interactions. And for each tool, we only require 20 minutes of real-world interactions. And that's sufficient data for us to learn a very accurate dynamics model, noticeably better than any physics-based models out there. And this lines of work actually inspired 2 lines of follow-up works, especially on learning large-scale like dynamical systems based on graph representations. Here are just some like interesting work on intuitive physics, batch-based systems, etc. This is on, for example, the graphics and the intuitive physics domain. And on the deformable object manipulation domains, here are just some other like follow-up works that really trying to also extend our framework, this graph-based modeling on many other deformable object manipulation tasks. So then, like after we have done all of these works, we essentially have this tool, this graph-based neural models, that we have this kind of hammers. We try to identify all the nails we can have. And this is what we have been doing so far. And we want to extend beyond that. Specifically, what's next is really trying to thinking about, obviously, more complicated tasks and more complicated objects, especially not just with like one type of objects, but heterogeneous objects interactions. And we want to scale up not just like on the tabletop domain, but all the way until this kind of in the wide data. Example like OpenX or Joint. And obviously, we want to build this type of engines, this kind of like a forward prediction model that can act as either data generation engines or evaluation engines, which can come hand in hand and can be very, very handy for the current developments of, for example, vision language action models. So looking back, we are actually like navigates over this kind of spectrums. On the left will be more physics, on the right will be more learning. And our graph-based neurodynamics model is somewhere in the middle. And on the left end, for example, on the physics side, there has been a lot of like physics-based simulators. Chuang have mentioned their Genesis, and also NVIDIA Warp, which is also described, for example, the physics-based modelings of the environments. And on the very end, on the right, will be this kind of learning routes, where people have been doing like a 2D, for example, action condition video predictions and trying to generate those videos and see how far we can push from there. So obviously, they all have their pros and cons. I don't want to reiterate them. But I also want to see, like, are there any opportunities in the middles? Do we have the right recipes that can marry the benefits of the structures, but also is easy and accessible for us to scale things up and be able to apply it all the way into the, in the wide collected data? So our trials, for example, more on the physics side, is this work called PhysTwin, which is essentially trying to use some kind of physics-based priors that enable us to build a digitalized versions of deformable objects that is both sample efficient and generalizable. So what we are doing here is that given a few seconds of real-world interactions, shown on the left, we can reconstruct a digital twin of this object. What we mean by digital twin is both the geometry, appearance, and also the dynamics of that object. And in the middle, what we're showing is our reconstructed geometries, and all the points on this kind of geometry are also tracked over time. And the points on the human hands represents the actions we are reconstructed also from this video. And the right video actually shows our resimulation results overlaid with the original videos. What we mean by resimulation is we only take the first frame as input, replay the actions reconstructed from the video in an open loop fashion on our digital twin, and we do action condition 3D video prediction. And we overlay that video with the original video. You can see it aligns very, very nicely with the original video. And here's like overall how the framework look like. Like the optimization is done both on the geometry, motion, and also the rendering loss. That represents this kind of object using a physics-informed modeling, specifically like spring mass modeling, that trying to model the dynamics of that object and using Gaussian splattings to model the appearance. And obviously, after we have these digital twins, you can just apply any novel interactions. And for example, here we have this kind of keyboard interface to do real-time interactions with this like deformable objects. It also applies to many other objects like stuffed animal, clothes, robes, etc. And in the robotics domain, we actually do real-time data collections about the robot actions and replay these actions both on the real robots and also on our digital twins. They are happening all at the same times. The left shows what's happening in the real environments, and the screen shows what happens in our digitalized environments. And this video essentially shows two things. One, our digitalized clothes is very accurate. The rendered video aligns very nicely with what's actually happening in the real environments. And second, our predictions is in real times. There's nearly no delay between our model's open loop predictions versus what's happening in the real environments. So this is because we implement everything using NVIDIA Warp, which can benefit from GPU accelerations. And we have also been pushing this direction forwards, trying to build this digitalized digital twin of this environment for this entire interactions and manipulation cycle. Here we replay the exact same action trajectories, both in the simulation and real environments, and they align very nicely with each other. The left is the simulation, the right is the real environments. And using this model, obviously what we can do is to do model-based planning. Here we show an example where the left is the target states, the right is our planned trajectories executed on the real robots based on our digitalized rope. Here's another example where the robots has to come up with some motions to do this kind of folding behaviors to fold the clothes that matches the target states. And obviously here we actually did some kind of constraining of our action space in order for the search to be effective. But overall, we're just showing that our model actually very nicely matches the dynamics of the real world that is able for the robots to do the motion planning. So on the left is actually more physics side. We're also trying to move forwards and trying to see if there's kind of more learnings we can blend in for more scalable, scale up of this framework, which actually enters our RSS paper this year, which is gonna be presented, I think, actually tomorrow or the day after. It is particle grid neurodynamics models. So remember, earlier I showed this video where we use graph as a representations to model objects of different geometries of different materials. And actually there are some very obvious limitations as we going through this process. Specifically, it actually requires expert knowledge in how to do the graph constructions. Sometimes the graph actually has to be constructed very carefully. The edges cannot be too dense or edges cannot be too sparse. We also need to have the right attributes on top of the edges and also the nodes for it to work effectively. And sometimes insufficient message passing steps would also fail to capture the global informations, especially if the graph is sparse or disconnected somewhere in the middle. And it still is a little bit limited in handling partial observations. More or less, we still assume to have reasonably complete geometry of the environments. So for example, for the dumpling one I showed earlier, although we only require, for example, the surface of this dumpling, but still we need some reasonably complete description about the geometries of that dumpling. So that is why we built these systems called particle grid neurodynamics model. It really is a method inspired by material point methods, where we not only relies on the particle representations of the environments, but also consider the grid representations of the environments, where we have this kind of point encoders and also this implicit fields that is able to do this kind of grids velocity decodings that's to do this kind of particle to grid transformations and grid back to particle transformations in order to predict the dynamics of the movements of each and every one of the particles. So essentially, this is a hybrid representations, and we are doing this particle to grid and grid to particles process to marry the benefits of both the grids and also the particles. And what we need really is just, in this case, a few minutes of real world interactions. And Kaifeng here is actually just doing random interactions with this rope using this robots. And these interactions will be collected. And we'll be first reconstructing the appearance and geometries of this rope. Here we are using Gaussian splattings. And then we'll be able to do action condition 3D radio predictions. Here on the top right is our actually a keyboard interface to model the behaviors of this end effectors. And this end effector is being end effectors movements is being real-time recorded and played on this kind of rope. And we'll be able to predict both the end effectors motions and also the rope's motions for this kind of 3D action condition video predictions. It also applies to many other objects like clothes, stuffed animal, and also boxes. For people who are familiar with dynamic Gaussians, I want to emphasize this is not dynamic 3D Gaussians. This is action condition 3D video predictions. Dynamic 3D Gaussian is essentially like a temporal interpretation. But here what we are doing is actually temporal extrapolations of like imagining how the environment is going to change when you apply like a novel interactions on top of this object. So this is what we investigated so far, meaning we have a very strong emphasis, as you can see, like things has to work in the 3D. Like if there are structures we can incorporate into the systems, we should incorporate that structure into the systems. And I have this belief that currently people are doing large-scale data collections for training this vision language action models. And many of this data, if you only using them for policy learning, that would be such a waste. Because there's a lot of like very rich dynamic information that's embedded inside those like large-scale collected data. And what we need for training those like policies is action condition robot interaction data. Now, if we need to train this kind of word model, is also action condition robot interaction data. So those data can actually be very, very nicely like used for us to obtain this word model that can be very, very beneficial for us to develop policies. Where the policy and model are just the two sides of the same coin. One is the forward process, which is the model, and the other one is this inverse process, which is the policies. So I'm personally very excited about the developments of the word model. It's just that we are still trying to identify the right recipe, the right amount of structures that is able to give us the generalizations and the sample efficiency, but at the same time can utilize all the in the wild collected data people are doing nowadays. So in the end, I want to thank all the collaborators, especially the like lead students like Han Xiao and Kai Feng for the remaining 2 works. If you have any questions, you should like definitely chat with them. They've been doing amazing works. Like without all the sponsor agencies and the collaborators, it would be impossible to do all these works. And I'm happy to take any questions now. Thank you.
Thank you, Yunzhu, for the great talk. You did amazing work and very extensive work. So one quick information before moving to the Q&A, we will also take the last oral presentation before the short break. Sorry for that. Having said that, do we have any question from the audience? Okay, maybe I can start. I think you've shown impressive results of especially like digital twins, neural simulators. I wonder, how does this work like with very highly dynamics movement, like for example, flinging, interactions with the object? Because what you have seen, you have shown seems like more slow movements. So any thoughts on that?
That's a very good question. So for more dynamic motions, so in general, like one of the key limitations I would say is about the current, like our means of doing like visual trackings. Because for the identifications of many of the model I showed here, we actually require some kind of tracking about the motions of the object. It doesn't have to be like complete full state tracking. It only needs to be like a partial trackings, like which is nice because there has been a lot of development on the visual foundation model sides. And many of the development on that side can actually be very nicely integrated in many of our work. For example, Face Twin is benefited from not only the visual tracking, but also the single image 3D reconstructions. But that I would also say is one of the limiting factors, because if the things move very, very fast, very, very dynamically, you create motion blur. That will create issues for those like visual trackers. But I believe like over time, that's just gonna become better and better of doing like tracking over these highly dynamic scenarios. Having said that, for example, for system that was like a more like physics-based prior, for example, this Face Twin, like even like our identification process like works in regimes where the movement are reasonably slow. But because we have physics priors, this kind of identified model can actually be used during the test time in high-speed regimes.
Okay, thank you.
Thank you.
Do you think like this could be maybe a sensing issue? Like we keep using RGB, of course RGB has a lot of information, but there exists also event cameras, right, which are faster, providing information and give information about the flow. So do you think like we should really stick with RGB, or other type of sensing, or like depth sensing could be the way to make it faster at least?
Yeah, that's a good point. So like for many of these works, we actually use steps for like 3D reconstructions. But you bring a very interesting point of using event-based cameras. So we haven't really done those, but I think that could be a very interesting directions to explore, especially like you mentioned, those high-speed regimes, like especially want to do high-speed trackings. And I think those sensors can actually be very useful in those scenarios.
Okay, let's thank again our speaker. Thank you.
Thank you.
Okay. Hi, everyone. Thanks for being back. I hope you had a nice coffee break, even if short. We apologize for that. So it's an honor to have Rares here with us. So Rares is a research manager at the Large Behavioral Model division at Toyota Research Institute. And his research spans robotics, machine learning, and perception, and in particularly emphasizes extracting visual representation for embodied agent. Prior joining TRI, he obtained his PhD at KTH, Royal Institute of Technology, where he worked on self-supervised perception and mobile navigation. So, Rares, the floor is yours.
Awesome, thank you so much. Can everybody hear me? Yes, okay. Sorry about the technical difficulties. I think, you know, there's always something in the beginning of these presentations, and I hate to be the person to be between everybody and their lunch. But I think we're good to go now. Seems like the slides are showing, Zoom is working. So it's awesome to be here. I'm going to tell you about our work on building structured large behavior models for dexterous manipulation. And this presentation is going to be split into two different parts. First, I'll talk about our work building LBMs, large behavior models, you know, what they are, how do we evaluate them. I'll show you some cool tasks, and I'll use this as a way to highlight some of the cool results we can get with them, as well as some of their limitations. And I'll use that as a way to motivate the second part of the talk, which is going to be about adding structure and inheriting some priors from other large-scale foundation models. Okay, I guess I don't really need to motivate this, but you know, we want our robots to do cool things, dexterous things. We want them to help us in our daily lives, in homes, in supermarkets, in factories. We want them to be able to do dexterous tasks and to have common sense and generalization. And systems today, they don't really generalize across semantic categories. You know, you have to sort of train them on lots of different data, and they have lots of different limitations. And the reason why we don't really have these robots in our homes today is because, you know, dexterous manipulation is really hard. Here's an example of a typical living room, not mine on a normal day, but sometimes. And you know, like this is just as a way to highlight some of the challenges that we have to deal with. You know, there are occlusions, lighting variations, various kinds of safety requirements, clutter, object variations, physical constraints, and so on. And robots, you know, for them to be able to work in home environments, they have to be able to deal with all of these things. And importantly, what they need is common sense, the ability to generalize across various kinds of categories, and also dexterity. And I want to take a second and define dexterity. So we've been thinking about this for a while at TRI. And when I say dexterity, what I think about is tasks that involve, you know, lots of contact, tool use, multi-arm coordination, precision. And here's an example of a particular task that I would say is sort of a dexterous task that I would want robots to be able to do. In this case, the robot has to unzip the Ziploc bag, lift it up, pour the contents from the bag into a bowl, and I would want it to do this autonomously. Okay, getting there. Yeah, so that's an example of a dexterous task. It would be great to have a robot in our homes who could do something like this. Another thing that I care about is long horizon. You know, so robots should be able to do things and that are not just atomic operations, but over a few seconds or even minutes. So here, the robot is packing this picnic box. It puts, you know, the most important things that we care about when we go on a picnic, a couple of Coke cans and some ice. But anyway, you get the idea. It has to pick something up with one hand, put it on the table, pick it up with the other hand, put it in the box. And so it's sort of long horizon dexterous task, which is another thing that we care about. Okay, so I'm going to give you just a brief overview about how we get these models to be able to achieve these tasks. So we start from diffusion policy, which is kind of a general recipe for behavior cloning. I think everybody's aware with the general setup, and diffusion policy was published a couple of years ago, and it really kicked in a new era of dexterous capabilities. And the setup looks something like this. We have an expert operator collect a bunch of demonstrations with a joystick or a space mouse or something like that, and this forms our data set. And we have images paired with robot actions, and we use the images as input. They're the observations along with the robot state, pass them to an encoder, and we use a diffusion decoder to generate actions that the robot can execute. And diffusion is awesome because it can capture multimodality, and it really enables dexterous kind of operation. All right, and there are some limitations, and fundamentally with diffusion policy in the single task setting, we basically have to learn everything from scratch. And that's obviously brittle. If there are environment variations, then we can't easily adapt to those. If we want to, say, learn how to manipulate an apple, and then we want to transfer that to an orange, that's not going to really work out of the box. And really what you get is what you teach. And if you want generalization, you have to add more demonstrations. And out of the box, you don't really get transfer very easily. And what we're interested in studying is how do we transfer dexterous capabilities from one task to another task, and how do they improve with these large behavior models? Okay, and I'm going to give you an example of particular model or class of models that we've been studying for quite a while at TRI. So we started with diffusion policy, which is kind of a well-known and understood recipe, and we scaled it up in the multitask setting. This is an example architecture. We basically did a couple of key modifications to go from the standard single task diffusion policy to multitask. We basically added the language encoder. We replaced the ResNet encoders with clip VIT. We concatenate everything. We pass everything to a diffusion transformer. So we got rid of the unit. It's not much larger, but it's something that is easy to study, and we know it has some limitations. But it's something that we understand fairly well. About 450 million parameters, so not huge, and it can be trained fairly fast. And this is one class of models for multitask behavior cloning. There are others. We know VLAs are sort of popular in the literature, and they borrow priors from pre-trained vision language models. There are also video LBMs, which is what I'll talk about in the second part of the presentation. And in the beginning, I'll just give you an overview of these kind of LBMs that are sort of scaled up diffusion policy and some of the tasks and limitations that we found with them. Okay, so we take an architecture like that. We've collected a fairly large data set, so 500 skills, roughly 500 hours, combination of sim and real. We have a mix of short horizon skills and long horizon skills, and we focus on high quality data. So this is an example, a combination of pick and place and more dexterous tasks, and this is what forms the training data set that we collected. And we combine this with external data from the internet. So we looked at the OXC dataset. We don't use all of it. We use a subset. It's fairly larger than what we've collected. So we do a batch balancing step. And that's what we use to train the network. And we oversample our own data because we think that it's going to transfer better to our own platforms because, of course, we collected it with the same platforms. And also because we think it's sort of slightly higher quality in terms of calibration and things like that. Okay, there are many different ways to study these LBMs, and we have lots of different results that we're writing up in a paper that we'll put on arXiv. For now, I'm going to focus on this particular setting where we basically start with a base model with initialized encoders. We train this model on the robot data that we collected in combination with the internet data that I mentioned just now, and we get a pre-trained generalist. We take that model, we look at an unseen task, we fine-tune it for that task, and then we get a fine-tuned specialist, and I'm going to talk a little bit about the capabilities of this fine-tuned specialist on some tasks that we designed. Before we get to some results and videos of robots doing cool things, a little bit about how we evaluate. So for each task, we do blind A/B tests in real, and we have controlled initial conditions. And the reason we do that is because there are sort of variations in the real world that we can't really control. For example, we might take a method, evaluate it, Monday this week, get 70%, evaluate it Monday again 2 weeks from now, get 60%, and we have no idea why the performance difference. It could be that someone bumped into the camera, or we evaluated in the morning first and now it's the afternoon, and things like that that we can't really control. So we do A/B tests, and we always compare our method with the baseline whenever we do experiments. Initial conditions is something that we design beforehand. So whenever we do a rollout in the real world, we specify this is the environment, these are the objects, this is how they should be positioned, and we have an overlay where an operator looks at the scene right now, the initial condition, the way it should be, and the operator sort of arranges things so that we control exactly for the experiment, and we can run both our method and the baseline under the same kind of conditions. And because we control things, we can also vary the initial conditions quite a bit. So this is an example for some simple tasks that we evaluate on. We change the object significantly, and then we can really look at performance along a few key axes that we care about in terms of robustness and generalization. Okay, so I'll show you a few tasks that we came up with, and the goal is to really push the capabilities of the robot in terms of dexterity and long horizon. And we wanted to find a balance between something that is very difficult, but that the robot can still execute and get some amount of success rate. So we don't want to be at 100% success rate. We also don't want to be at 0% success rate, because it's tough to learn anything in the extremes. We want to be sort of in between 20, 30%, something like that. Okay. So here's an example of a fine-tuned long horizon task. You'll see the LBM on the right and the baseline that we compare against, the single task on the left. This is a long horizon task where the robot basically has to set a breakfast table. And it looks like a bunch of individual skills, but actually the whole task is sort of demonstrated as one continuous demonstration. And then the robot has to learn how to execute it. This is the set breakfast table task. And we see that the LBM is sort of generally more dexterous. It doesn't always succeed very well, so it keeps trying to pick up the apple. But based on introspection, we find that even when it fails sort of more gracefully, and then it learns how to recover, and it keeps trying in a way that is more natural than the single task baseline, which is which still executes the task, but it's generally less accurate, and sometimes just fails. Okay, that's one example. Let's look at another example. This is maybe one of my favorite tasks. So this is autonomous, by the way. We pre-trained the LBM, then we fine-tuned it for this task, and then we let it execute. This is, whenever I see this video, I'm kind of impressed that the robot can do this. So basically, we have a bike tire, and the robot has to pick up this rotor and put it on the tire, and then tighten a bolt with the spanner. And so you saw it dropped it by mistake, and then it went and it picked it up. And this is all autonomous, sort of learned from data, these recovery behaviors. And now it's going to try to fit it in, pick up the small part. Okay, fit the small part. There's quite a bit of moving around to do to make sure that it doesn't fall, which, by the way, happens quite often. But sometimes it succeeds. Okay, then it's going to put the spanner and then tighten this bolt. So this is an example of a task that requires not just long horizon execution, but also quite a lot of precision, right? Okay, I'll move forward to show you one more, which is also quite impressive, I think. So here the robot has to cut this apple in slices. And first it has to remove the core. So we call it the apple coring task. This is also autonomous, by the way. So it's the same LBM baseline model that's fine-tuned for each one of these tasks, and then we let it execute it. Okay, it's going to pick up the knife. Yeah, there was a lot of fruit wastage that day, but, and yeah, I mean, there are many delicate steps. It has to take the knife out of the sheet. It has to cut the apple in half, turn it around, slice it. You know, but generally it looks like we're seeing some very interesting signs of life in terms of dexterity and pushing the boundaries of what these robots can do. Okay, it's going to slice it, then move it to the side. Okay, slice the next one. You get the idea. Okay, so qualitatively it looks very impressive and very interesting. Those are sort of some of the better rollouts. When it fails, it's not, you know, it keeps trying in a way which is natural, which is very interesting. So we're trying to introspect and analyze exactly where those behaviors come from, how to incentivize the model to learn more recovery. We also have quantitative numbers. So this is a way to show success rate, these violin plots. I'll go a little bit through the details of what's happening here. On the x-axis, we have a few of these long horizon tasks that we designed to be sort of complex and difficult. On the y-axis, we have the success rate. The violin plots are a way to show the posterior over the success rate, and the success rate is the parameter P of the Bernoulli distribution that generates success failure. So we do a Bayesian analysis. I think it's more informative than just box plots with confidence intervals. And we also look at task progress, which is basically generated by having an operator look at the rollouts and saying, okay, in this case, the robot did 5 out of 7 steps, so we get, you know, whatever success or task completion metric. And so on the left, we see the success rate is as expected, in some cases around 40%, in some cases around 10%. But anyway, we're seeing the robot starting to execute these tasks reliably. And despite the slightly low success rate, in terms of task progress, we get quite far into the task, both the baseline and the LBMs. Okay, going to change gears a little bit and tell you a little bit about new and exciting work where we're trying to basically overcome some of the limitations we're seeing with LBMs. So if we take a look at these results again, we see that success rate is quite low. This is, you know, it makes sense. We designed these tasks to be difficult, and we are, of course, trying to improve the model to get better success rate, get better at executing these tasks. And we know we have to think of ways to deal with dynamics in the scene, because these tasks can be quite complex, long horizon, occlusions, contact, geometry, and so on. Another thing that I didn't mention here, but a known limitation, is if we try to evaluate the generalist model, so the LBM out of the box without fine-tuning, it doesn't really transfer to these long horizon tasks. So this is also something we're looking into, and something that we hope to get out of structured large-scale foundation models. And to overcome some of these limitations, we started looking at video models for robot learning. And we look at recent advances in video generative models like Google VO2 here, or OpenAI Sora. And we see that they're quite impressive, and they highlight like very exciting advancements in building foundational models that capture dynamics and the effect of actions in the real world. And this is something that we want to evaluate and introspect and see how can we transfer these priors to actions. And we've put together a paper which is actually under review, and it's kind of early work in this direction. It's called Video Generators Are Robust Robot Policies. It's in collaboration with colleagues from Columbia University. And we investigate how to combine video generation and action generation in a modular framework that can be trained end-to-end. And I'm going to tell you a little bit about how this is set up and early results, which look pretty exciting, I think. So the goal of the paper is to see if we can turn video generative models into policies. And we actually show that the video models already have quite a bit of information, and they can easily be adapted to be policy generators. And not only they can output actions, but they also generalize in very interesting ways to new environment configurations, new objects, and also new tasks, which is something that we hope to borrow and that we'll use to improve our LBMs as well. Okay, so here I'm going to show you an example. The rollout is on the top, and the video prediction, so this is the output of the video generating model, is on the bottom. There will be more videos. The video generation models takes about 7 seconds for inference, so that's why it sort of looks a bit out of sync. But generally, it follows the rollout and the execution trajectory quite well. So just a very brief overview about how this works. As before, we start with a set of demonstrations, which we collect. This forms our data set. We have paired images and actions. We use the images to fine-tune this a video diffusion model, which we have. We use it pre-trained. We use stable video diffusion here. We extend it to also take language conditioning, so we can steer it with respect to a particular task. And then we have it generate video based on the first frame and the task. And at the same time, we train a video adapter and an action decoder, either jointly or afterwards. And we condition this with noise, and then we generate actions which can be executed on the robot. We use RoboCasa first for evaluation in simulation, which is great. We can do lots of experiments. People who have used RoboCasa are familiar probably with the setting 24 sort of atomic tasks that we use to benchmark the performance. We use the standard benchmark. We use only the 50. So there are many different settings. We use sort of a restricted regime in terms of demonstrations. We compare with a few state-of-the-art published methods. And it seems like our method works quite well, even though we use few demonstrations. DP-ResNet and DP-Clip are sort of baselines that we implemented. They're just vanilla diffusion policies scaled up for multitask. And we have a few very interesting results in addition to this that I'll go into, which I think highlight the power of these models and the kind of transfer that we get from them. So in addition to the average results, we looked at why does this work and how well does it work, and what's the interplay between action and video generation. So we looked at a few different ways of training this model. So on the bottom, if we don't do any video training, then it doesn't really work so well. It doesn't generalize, so we can't just add an action decoder on top of a video generating network. Out of the box, it doesn't really condition on our images from RoboCasa. It doesn't really generate high quality videos. And so it turns out that adapting the video generation for this task is actually quite important. And there are two ways of doing that. We can do joint training. So we take the RoboCasa demonstrations, we fine tune both the video and the action. And that interestingly works worse than if we do two-stage. So we first fine tune the video generation, and then we freeze it, and then we fine tune or we train the action generation. We found that the two-step way of training actually works better, which is quite interesting. We also looked at video prediction horizon. And it turns out that across all the different thresholds we looked at, if we increase video prediction, the quality of the action generation increases, and we measure that by success rate on the y-axis. And in all of these cases, we kept the action prediction horizon fixed to 0.8 seconds. And this highlights the importance of modeling dynamics accurately and the interplay between dynamics and action. We also looked at using action-free data. I think this is probably the most exciting result. So we have 24 tasks in RoboCasa, and what we did is we split this set into 12 and 12. We trained the video generation on all 24, as we did before, and then we trained the action generation just on the first 12, and then we evaluated on all of them. And we saw that there wasn't much of a performance drop. So even though we didn't train on all the tasks, we could get generalization to the unseen tasks out of the box, which is very exciting because it highlights the ability to use action-free data to learn priors, which then transfer to actions. So we looked at this, a couple of tasks that we hadn't trained on and we evaluated on: turn, sync, spout. Again, you see the video prediction on the bottom and then the actual rollout on the top. So this is something that we haven't trained on, but it's generalized quite well too. We also looked at pick and placing to counter. There's lots of different ones that we checked. The interesting thing is we haven't trained the action predictor on these, but nevertheless, it kind of worked out of the box via transfer from the video backbone, which is very exciting. Oops. Okay. We also looked at the quality of video prediction with respect to action success. So it turns out that there's a strong correlation. If the video prediction metric indicates high quality video prediction, that correlates with successful rollouts, which is exciting because it means as these video models tend to, as they will get better and better, which I'm sure they will, we should be able to leverage that for action prediction. Okay, we also did a few real world experiments. So this is early stages. We collected data, 200 demonstrations for a few different tasks. Maybe I'll go quickly through this. We put together a set of 5 tasks: open drawer, pick and place, put M&Ms in cup, upright objects, stack ups, just to basically understand what kind of transfer we get from these video backbones in the real world in addition to simulation. We controlled the training conditions, and then we have sort of separate testing conditions that I can go into the details offline. And what we really wanted to study here is generalization. So do we get the same kind of transfer from the video backbone in the real world as we saw in simulation? And we looked at a few different axes. We varied the object location. We looked at new objects. Can we manipulate them? We looked at unseen backgrounds and so on. And indeed, we get similar kind of transfer to what we measured in simulation. And the robot is able to manipulate unseen objects, which is something that we hadn't seen before. It can adapt quite well to unseen backgrounds and so on. And here are a couple of very quick examples. So in this setting, the robot is going to pick an object that it hasn't seen during training and then put it in this bin, in the cup. Okay, and similarly, we'll do the same with an unseen background. Hopefully it's going to play, yes. So the background is different, and we get this kind of adaptation despite the fact that we train on sort of few demonstrations thanks to the power of the pre-trained video backbone. We have lots of these videos for all of the tasks, and we describe in detail the test and training configurations. Okay, so to very briefly conclude, we looked at LBMs, and we saw that the way we train them and the way we evaluate them, we're starting to see that they enable dexterous manipulation on more and more complex and long horizon tasks with some limitations. So we need to do this fine-tuning step. I didn't go into the details of evaluating them zero shot, but there are some limitations there. And we're looking at ways to overcome those, both to improve the success rate and also to get this kind of generalization outside the things that we trained or fine-tuned on. And for that, we looked at structured foundation models. And in particular, we saw that video generators are robust policies. So sort of out of the box, they encode very powerful priors. And when we fine-tune them with actions, we get them to perform well on the tasks that they're fine-tuned on, and also generalize to things outside the training set, which is very promising future direction that we're working on integrating into the main LBM system and exploring further. Okay, thank you very much.
Thank you, Rares, for the great talk and for sharing some of your recent results. Any question from the audience?
I think I'll go for the kind of more higher level. I think you're probably the person I've seen the most do demonstration, learning from demonstrations, and like a really wide variety, and then you're doing long-term. What's your take long-term for robotics? Is this how you're thinking about we're gonna go about and have robots in our house? Is it all based on demonstration? Like, what's your ideal model, like system model you would like to see?
Yeah, okay, let me repeat the question. So how do I think about getting robots in the homes, and what's the path to getting us there? Is it scaling up demonstrations? Is it something else? Yeah, I mean, there's a lot to say to that question, but I think it has to be a combination, right? I think we definitely, so first of all, I think if we want to have a robot work really well for a particular task, right, to get a specialist, I think we probably have to train a generalist first on many tasks and then do adaptation on any one particular task. And that's going to have a higher chance of success than just, collecting 10,000 demonstrations for just one thing, because that's going to be very brittle. And then in terms of sort of general purpose robots, I think scaling the data is important. So diversity of tasks, I would say, much more than, task specific data, and also borrowing priors from things that we have seen sort of work, so from existing foundation models, right? So language models, vision language models, video models, they encode quite a bit of interesting information and generalization in terms of semantics. And I think that also has to be an ingredient. So a combination of real world data, I think diversity is important, as well as pre-trained models that we've seen, actually can do quite some interesting things.
Thank you. Maybe one last question while the speakers reach slowly. Please, I invite all the speakers to join for the panel discussion while we get the final question.
Yeah, great talk. I watched that the bike wheel, experiment. I watched it live when the robot was succeeding. It was really cool. So yeah. way nicer than watching these videos. So I have a question about that. Oh, it was actually important that we see the slides.
Sorry. Okay. Now that's going to be difficult. We might have to wait.
Okay, whatever.
We might have to wait 10 minutes to set up the. Let me see.
It's fine. It's fine. Okay. So it was okay.
Okay, we're back.
So there was like a slide on the success rates.
Yes.
And I noticed that, like, when it comes to the bike wheel experiment,
yeah,
it looks like the specialist is better than the fine-tuned LBM. Is that true? Like the leftmost?
Yeah, so it's difficult. Yeah, it seems like based on just the average of the violin plot, one seems higher. I forgot to mention, thank you, okay, this is good. The letters indicate whether the two are separable with statistical significance. It's based on a sequential A/B test. So actually, despite the fact that it looks like one is better, we can't really say with 95% confidence whether one is better than the other. But it does happen. So the LBM method isn't always better. It does happen that sometimes just fine-tuning, just the single task method is better. It depends on sort of the diversity of the task and how we evaluate. And this one is kind of, like it's long horizon, it's dexterous, but the wheel is there. There isn't a lot of diversity in terms of, at least not in the way we evaluated, right? A lot of diversity in terms of distractor objects and things like that. It does happen. So we're trying to understand why.
All right. Okay, thanks.
Let's thank again our speaker.
Thank you.
Okay, cool. Yeah, so for the panel, the format will be very simple. We'll prepare a list of questions that hopefully most of us will be interested in. And for the sake of the panel, I know everyone is super nice, but just for the sake of panel, please try to be adversarial a little bit, and then of course to give your best hot takes. I'll also frame my questions in a probably more adversarial way, although we all agree that world modeling is an important topic in the community. All right, so first and foremost, I guess, what is a world model and how do you define it? Yeah, that's... I guess...
Sorry. I guess it's easier for you.
Okay. Yeah, take this one.
Yeah, okay, so I'll start. What's a world model? This is an excellent question. So, I mean, we used to think that this is an next timestamp function, current state and action, give me the next state or distribution of next states and so on. Well, for sure, this is a part of it. It might be that it's something much more diverse and multimodal. For example, one way that I always think about things is I look at more advanced robots, for example, self-driving cars and how they got there, and they didn't use video generation models and so on. So it could be that the next generation will do that. We'll just train a big, video generation model and search over actions in that beautiful universal interface of pixel prediction. But what they did is, in fact, they have something much more nuanced reasoning there, like what is the relevant objects, where they're going to move, what is the situation, what are the relevant signs, the traffic lights, and so on and so forth, what is the relevant memory I need to retrieve potentially to put the correct reward function in the scene and so on. So I would imagine that eventually something like that might be relevant for robots as well, a little bit more nuanced reasoning, and some part of it will be, a next step function or in pixel space or in motion space or some other, or both actually, yeah.
I think the definition should be action conditioned future prediction. But action here can be quite broadly. So initially, people talk about action is the real physical action, but now it can be more broadly. For example, text to video, text control can be action, or that kind of camera control. For example, the virtual camera have that kind of camera control can be action. So that is what I think about world model.
Yeah, I think along the same lines, so some kind of a compressed spatial temporal representation that captures, can be conditioned in a broad set of ways. I often think about conditioning based on images. I think, like that's close to what I've worked with the most. Could be text also, and then the ability to forecast what happens next, modeling dynamics, interactions, counterfactuals, what if I were to take this action, that action, sort of the ability to imagine the future and then reason in the space of possible futures. I think all of those are kind of properties of world models.
I'm going to be adversarial. You guys are thinking too much about the action conditioning. I think you should be also thinking about anything that allows us to understand the world. Like earlier we've seen LLM being used to give us like some grounding on how big is a cauliflower and how heavy it is. I think there's a lot going on with trying to ground our reasoning into things that make sense. Also had to add how these models can allow the robot to be creative, answer questions, think about the possibilities. So,
okay, let's do some fun stuff. So I disagree with that one. So I think there's a distinction between world knowledges and world model, and people always mix them together. I would say world knowledge does not. I would say the difference of world knowledge about okay, image reasoning and dynamic reasoning. I would say they are completely different according to cognitive science. The world model is really inspired from human mental model that understanding. So if you really read the cognitive literature, that's for example, Jordanova or whatever they're writing about is really about physics simulation as approaching the world model, human mental model. So I would say if there's no dynamic, it would be hard to say this is kind of world model. But of course, for robotics, world knowledge can be useful for anything, but it's just not the world model.
all right, you can go ahead with that.
Yeah. Thank you, everyone,
for
the opinions. I love the discussion. Yeah, and I guess related to this last point, many of you mentioned like future prediction, and I know that there's a lot of different definition of what could be the future, and you all in your talks mentioned about it. So but one big distinction is whether it's explicit or implicit, and whether it's 3D or in 2D. So yeah. So what's your take on this?
Whoever solved robotics gets to decide. Yeah, I would say like anything that would make it work, right? I don't like learning from demonstrations, but I've seen amazing things about putting a bicycle wheel together, and I have to recognize that it looks amazing and it looks really good. But yeah, you should solve robotics, you win.
Yeah, so I love the question implicit versus explicit because like 2 years ago, for example, in vision language models, we would have a scene and a super complex question. For example, how many people, wear a blue shirt and they're sitting on the second row, and then the output would be 4. And then we'll say, oh, this is great. The model does this implicit reasoning through the attention layers, and we were super happy with that. But recently, we have made this reasoning more explicit, right? Through explicit chains of thought. Oh, let me go to the second row. Let me see how many people. Oh, yeah, these and these have blue shirts. Let me add them up and so on. So we go from implicit to more explicit. So I think the same thing could happen with this world reasoning, that we do need something more explicit. I want to mention something about word knowledge versus word modeling. I do believe that things are a little bit blurry. Let's say you go in a 4-way intersection. It is word knowledge that, the person that arrives first goes first. That's how the rule works. I mean, this is world knowledge, but also influences the dynamics and how you're going to behave. So that's why I think like the world model may be something very complicated and very, let's say, heterogeneous. But much like this super multimodal, chains of thought, even more multimodal, latent, explicit, employing tools from computers for 3D computer vision. I can totally see traditional computer vision of orientation estimation, object detection, pose estimation, and everything being tools on this, chain of thought pipeline. And the other thing I want to mention is that as we transition from novice to expert, there is much less of this intermediate reasoning and much more, reactive, behaviors. And you can see this from the Formula One drivers, how they park. Like they don't go back and forth at all. They just go directly to the spot. And this directly shows how this transitioning happens. And we all the time need to think and go back and forth and so on.
Yeah, so I think that's a good question. Actually, there's another formulation of this one grounded more in cognitive, that intuitive physics or that kind of analytic physics. So basically, intuitive physics. So basically, when we solve the problem, that sometimes actually we don't need to really write down the physics equation to solve the problem. For example, the example I showed in my talk, there's two balls, which is heavier. Actually, you have some physics knowledge, or even you do some tasks. Actually, you're trying to imagine what's going to happen now. What will happen next? This kind of stuff, you don't really write down the equation to calculate, okay, what will happen next? But I'm trying to grasp a bottle that don't need to calculate what kind of exact action and based on physics equation, how to do that. The human don't do in this way. But we do have the kind of physics knowledge. It's more like to explain what we have seen before. So in this part, we probably need to have some analytic physics. For robotics, I feel it might be the same, that I would say that kind of implicit physics or analytic physics is more like trying to, like a data creation. And once we have a lot of data, that probably everything, we might be able to learn it in that kind of more implicit or neural way, I would say. Yeah.
Okay, in terms of the representation, maybe I answer the question slightly differently. I definitely think it has to be implicit because we have, we don't have direct supervision. We don't know the equation for the world model. And we will, I think we'll supervise the world model via proxy tasks. So you mentioned pixels versus 3D. I think supervising with pixels is probably the wrong objective, but we have so many of them that we have to use them. I also think 3D is important. So, what is encoded by the world model is, like something that we can guide the kind of properties. And I think about 3D a lot because it's close to what I've worked with for many years. So, the ability of having a world model that's encoding useful properties in latent space and from which we can decode interesting things, like images. So we can supervise because we have so many videos and they encode useful things. 3D, viewpoint, objectness, all of these are sort of important properties that I think the world model has to capture implicitly, and we have to be able to, if we can decode them, then it means that we've encoded them in a correct way.
Yeah, thanks for the, Sort of some thoughts. When you use the LLM, you can be very expressive, and then you get also very expressiveness out. And then when you're teaching someone a task, like you're not really holding their hand specifically how to move, but you'll provide high-level feedback. Have you guys ever thought about that sort of expressiveness, but also that sort of way of like providing feedback? I don't know if I'm just wondering.
Yeah, I think, in fact, I'm not 100% sure, but Tesla did come to CMU campus like a few months ago. And in my understanding, the driving models do talk and do analyze the situation and say, we're in this situation, he needs to go first. Oh, I need to do this and so on. So I'm pretty sure this is already, used actually everywhere. And I'm pretty sure we're going to see robots reasoning much like VLMs reason or LLMs reason in like everywhere in the next 6 months.
Right. We can move on to the next one. Okay. Why do we even need a world model, especially in the current kind of era of end-to-end approaches doing so well? For example, I TRI the LBM and also the VLA models from physical intelligence, Google, NVIDIA. Why do we even need to think about world models?
Yeah, so I think we're starting to see more and more really awesome dexterous behavior, but transfer to new tasks, generalization, that's still something that we are trying to enable. And like a very interesting area of research or direction we're looking into is, let's look at foundation models for language, VLMs, video. They you see what Sora generates or Google VO2, and clearly they encode some very powerful priors. So I think there's a role for those, and we're trying to figure out how to get information out of them and transfer it into actions. And another interesting area that I think is going to become more and more important is for evaluation. So action conditioned video generation is going to be something that's going to be more and more important, coupled with a VLM that would say, okay, for this, let's say I want to execute this tasks. I have a policy. The policy gives me an action based on an image. I plug that into the action condition world model, get the next frame, feed that back into the policy, and sort of create a feedback loop. And then I analyze the success or the failure of the policy. I think I've started to see papers that explore this more and more, and I think that's going to be quite important in the future for evaluation. Evaluation in the real world is very, very expensive. And so, we use simulation whenever we can, and using world models for evaluation, I think, is going to be very, very important in the future.
Yeah, so I think the question about end-to-end learning and world model, they are actually not that kind of conflict with each other. But I do think, for example, the VLA stuff that compared with SWOMO, I think I would say there are something fundamental wrong about the VLA. Is that I never understanding is that why we need using a language model as backbone for learning the vision language action model. And I really talk a lot about mention that, and also we also think the same, is that essentially I think so if I want to buy it, I would buy the VLA should be the video model as a backbone. One reason is that because for a lot of real world tasks, you need to imagine how to do that, and you probably need to train on a bunch of data to save up. And the language model they don't really, so I don't think language model really learn about how to pick up objects, how to do things in the real world. But the video model actually, they actually learn a lot of stuff, how to do things in the real world. And we do see there's already some ongoing, so for some work, for we have been working at called Tesseract. We just showed that you're just using a 1B, 2B video model and then learning on 3D, 4D, actually the policy learning can be generalized very well. And also I think Schwartz group also has a unified video action model. And also he learned that he worked on visual language planning. So I do feel the video world model might be the final answer for that one. But the reason that why the vision language model a lot of people are working on that. One reason is that we don't really have evaluation benchmark to say whether VLA or video model, which one is much better in open world scenario with generalized better, which one is generalized better. So Genesis is trying to create some this kind of benchmark, but we are still on progress. So that part we are not clear what is the generation, how can we evaluate. But for me, I will buy the video model actually can be much easier to generalize. Another reason that the language model right now is more like a convergence, more like they are slightly performed again. But if you see the progress of video model, every month, the model performance actually they are substantially improved. If you see what happened last year and what happened this year, you just see the result improvement. I would say the space of improvement is huge. I mean, the upper bound actually I can imagine huge. So that's why I believe that the video model might be the final answer for the robotic foundation model.
Yeah, so let's try to understand what is end-to-end learning. So if I tell you clean up the auditorium, maybe what you have in your mind as end-to-end is that, this text instruction will come, and then a huge stack of attention layers, and then the actions will come out one by one. I mean, this is very, very difficult, right? You really need to have cleaned auditoriums multiple times. This is a super long task, so this probably is not going to work. So that's one thing I want to mention. The second thing is, what is a world model? We can predict the future in multiple different modalities. For example, for far away, text prediction makes total sense. I mean, I can totally verbalize what's going to happen. You know, all of you guys are going to leave the auditorium. I can even ground it, like I can ground it in trajectories you guys are going to follow, and you know your orientation. Probably you're not going to walk backwards by looking at the screen, right? So I can generate pixel predictions. Probably not. I mean, I could if I had insane resources, but why would I do that? I mean, that I'm just by paying GPU and yeah, other resources, let alone to train those models. So I do believe that we're going to use all of those future predictions in text space, in sparse multimodal space, in motion, explicitly motion, because sometimes motion matters, sometimes appearance matters, like when you want to prepare a recipe, etc. And all of those will be used to decompose the task into subtasks, and all of those will be used as sub-goal condition for, you know, your end-to-end models, and they're going to decompose even further and even further till, you know, your action prediction can handle those. Yeah, so this is what I build, and I think this is the world model. The fact that, you know, a long task can be decomposed into things that I can handle. Yeah, in that sense, it's pretty general. Yeah, why we need it? Because it generalizes much better than the end-to-end approach. So yeah, so maybe this is.
I'm a big fan of the Matrix. Like when Neo gets plugged into the Matrix and gets to learn Kung Fu. I think there's a nice parallel here to say that if you have a world model and I want to learn Kung Fu, then I can plug myself into it and then learn in a safe way. There's a parallel to how these reasoning models are trained, right? So if I can think about generating traces and I don't have any issues generating them, I can be in a safe space learning different set of skills as a robot. So it's very exciting. I think all that space is passionate. Yeah. Thank you.
Cool. Yeah. So we actually have a few more, but we want to give the audience a chance if you have any questions that you want to ask the speakers. All right.
Right, thank you. I want to just ask the panelist one question because since the organizer also mentioned there are two ways achieving world models. One is really physical-based simulation. The other is data-driven generative models and so on and so forth. So far, and also implicit and explicit. So far, those two directions, they talk with in very different languages. Our goal is always, you know, we want to try to combine the best of two worlds. But it seems to me that we haven't really figured out how. I'm wondering whether you have some insights about in future, you know, is that necessary that we need to combine both? And if possible, if needed, and how we try to achieve that?
Is the question about the different, like, why are we talking about simulation and the real world differently?
The question is about how to combine physical simulation and generative model, if and whether it's needed.
Yeah, this is a fantastic question. Yeah, so right now we're going to put the world in simulation in the physics engine and try to use the data from there, or we're going to have neural models and these don't talk to one another a lot, right? Or we try to get them to talk to one another, but you know, it really hasn't worked very well yet. So I believe that eventually nobody is going to be using physics engines. Everything will be neural, let's say in 10 years from now, okay? Because we humans, for example, like I love this example, we know what we can swallow and what we cannot swallow, which is super important, by the way, because you can get drowned if you try to. And we don't have any physics of our throat, etc. We have a very intuitive, data-driven idea of what we can manage and what we cannot. So I believe the same thing is going to happen. So, but in the last part of my talk, I mean, we can use physics simulators as supervisors to train neural models in terms of motion, for example. For pixels, we don't need them because we have a lot of high quality data, although even for pixels, you know, all the video models do use a lot of simulators to train. So one way to think about it is that physics engines will generate training data for generative models of motion or of pixel appearance. Yeah, and another way would be that generative models will generate environments for physics engines, because without them, the physics engines are empty, right? So we want to see the scenarios into actual real scenes. So there again, generative models is a way to go from an image or a video to a reality that can be simulated in the physics engines. So in that sense, there is a lot of back and forth between the two. But eventually, I would like to see much more machine learning in the physics engine. Why would we wait for the solver to tell us where all the particles are going to go? We should be able to take care of those with neural modules and try to add some learning into the step function of the simulation. I feel like there's quite a bit of opportunity there that people are not looking into yet.
Yeah, so that's a very good question. And also, I think Professor Shenlong Kuru has worked a lot to kind of deep integrate the physics engine and the generative model. Actually, I'm a big fan of this line work. And also, I feel this is a really good science. And in the future, I somehow agree with Katerina. Probably the ending point of all the kind of world model probably will be the kind of purely neural-based model. It's similar to the large language model that the people have working on parsing analysis, but eventually they're all gone. It's one transformer on. So moving forward, so even I work a lot on physics simulation, but I can predict in the long run the eventually format that would be a neural model. But doesn't mean that the physics simulator will not play a role here. So I will see there's a few directions that physics simulator can be deep integrated that kind of video generative model training. One perspective is about, Katerina already mentioned, is about synthetic data generation, how we can generating the data with much controlled, with much controllabilities with another additional 3D, 4D, that kind of information that can provide additional information for them, even for the video post-training or job training, whatever kind of stuff, that kind of synthetic data, for example, even for them in some camera control, that kind of stuff, that you want to do some fancy stuff, you want to add in more inductive bias and using some synthetic data, I can see simulation play a role in this part. But ending effect is still neural model, but it's just that you have another different data and some fancy technique like control network to do that kind of controllable world model. In the second part, I will see the speed simulation could be very useful is for the reinforcement learning for video model. So essentially, you can always use the physics simulator as a feedback or as a verifier to do the kind of test time scaling and enable the video generation much physical possible. But essentially, this is still neural video model, but you're just adding another physics layer actually help them to adjust the model behavior. But I honestly don't see that there will, imagine 5 or 10 years ago that the best video model will be some PDE model or physics informed model. I feel it's a good science, but I think that the data-driven probably won't be very easy to scale up. So that's my guess. Yeah.
Yeah, that's an awesome question. It's difficult to say for sure. I mean, I think everybody believes that there's going to be sort of a union of the two at some point. But I think for a while we'll have to use both because, like when we evaluate LBMs, we do real world evaluations. They're super expensive. We use simulation, which is great, but it's not perfect, and it's not always a very good match for reality. But on the other hand, we can simulate. We use Drake. We can simulate quite a few things. Drake has this awesome hydroelastic model for deformation and contact. There are other simulators that can simulate things very quickly. Simulation has a big role to play in the way we evaluate. I'm very confident that world models, like the ones that we saw, are going to have a big role to play for evaluation in the future with policies in the loop. And, I think they're going to continue getting better and better. Maybe we'll use physics simulators as a way to supervise them, like Katerina was saying. I'm sure that's going to play a role. Probably at some point converge towards what's happening in rendering, where we use learned rendering. So not everything is, or I forget exactly what the math turns out to be, but maybe we calculate one ray and we use learning to approximate 10 or something like that. So there's going to be sort of a gradient of dialing in more and more learned components. Maybe at some point we'll have purely learned world models. I don't know. I mean, yeah, I'm bullish on that, but I don't know what the timeline is. How we're going to get around issues that we still see with language models of hallucinations and things like that, where the physics don't really match the real world. Yeah, at some point maybe they'll fully replace physics simulators. I don't know when that's going to happen.
Is there a difference if you're simulating from a model that you can predict or a neural network model? Eventually it might just become I'm simulating, right? How? Curious to see how it's gonna behave with the future. Maybe our kids are gonna say, yeah, I'm simulating stuff and it's using a world model. But I feel like if I'm looking at video games, people are gonna still want to have like deterministic simulators.
Cool. All right. Love the discussion. I think also time is up. And let's thank the speakers again for their participation.
Thank you to the organizers. Thank you so much.
All right. And and I guess we will actually have a closing remarks and also announce the award for the paper as well. But yeah, Kaifeng will take over from here. Okay.
Hello? Okay. Awesome. So yeah, this is the closing remark and the award session for our workshop. Unfortunately, we are already over time, so I will try to do this very briefly. So just to do a brief summary, our workshop has accepted 14 papers, and I actually did a very cute word cloud of the workshop paper titles, and we can see that we have very diverse paper topics spanning dynamics learning, simulation, video model, manipulation, and all the relevant topics. And a lot of interesting, very insightful papers are accepted, and these exciting results are all from our accepted papers. So we had 4 oral papers which had very high review scores, and previously we had already heard their presentations. They are FLAIR, robot learning with implicit word models, WOMAP, word models for embodied open vocabulary object localization. I guess I need to. Yeah. One-shot real-to-sim via end-to-end differentiable simulation and rendering. And finally, DAIWA, diffusion policy adaptation with word models. Let's congratulate those papers authors again. And among all these 4 papers are very are wonderful works, and among them, unfortunately, we have to select for one to give our best workshop best paper award to. So so now I will review this award. The best paper award goes to WOMAP, Word Models for Embodied Open Vocabulary Object Localization. Is the author of this paper here? Okay, yeah, because we are over time probably. And yeah, it's unfortunate, but there's nothing we can do about it. Also, thanks for all the other oral presenters that are here till the very end. I think we had a very insightful discussion, and we all enjoyed the final discussion session of all the speakers. So finally, we also want to thank all the speakers for their discussion and their very interesting talks, and all the organizers of this workshop, without whom there won't be such an interesting discussion. Yeah, and oops, accidentally turned on the video. And that's all for our workshop today. The paper list and the workshop recordings will be available on the website. So are there any final questions? If there's not, then let's conclude our workshop here. Thank you everyone for joining. And thanks for everyone that's listening online. Thank you.